September 26, 2025. 4 days ago. The date now sits in the archives of space weather databases, but its implications continue to unfold in real time. At 14:37 UTC that Thursday afternoon, instruments aboard GOES-16, a geostationary satellite monitoring the Sun from 22,000 miles above the equator, registered a sudden spike in X-ray flux. The event lasted 11 minutes. Solar physicists at NOAA's Space Weather Prediction Center in Boulder, Colorado, flagged it immediately. An M-class flare, moderate by solar standards, erupting from active region 4232 near the Sun's equator. The plasma burst traveled outward at 1,000,000 miles per hour, a shockwave of charged particles expanding through the void. Within hours, the flare triggered a coronal mass ejection. Billions of tons of solar material, electrons, protons, magnetic fields, peeled away from the Sun's surface and began the 3-day journey toward Earth. Forecasters issued alerts, power grid operators prepared, amateur radio. Enthusiasts anticipated disruptions. This was routine solar weather, the Sun's temper tantrum, predictable and familiar. But something else happened that night. Something unscheduled. 3,000 light-years away, in the constellation Cassiopeia, a white dwarf star, dense as a city compressed into a sphere the size of Earth, suddenly brightened. Astronomers call this event a nova, a thermonuclear explosion on a star's surface, fueled by hydrogen stolen from a companion star over centuries. The nova, catalogued as NovaCas 2025, flared from invisibility to naked-eye visibility in less than 12 hours. Its light, traveling across the galaxy for 3 millennia, arrived at Earth on September 26th. The same day, the same hour. Coincidence, perhaps. The universe is vast and events overlap by chance. But then came September 28th. 2 days after the solar flare, Comet C-2024 G3 SWAN, a ball of ice and rock discovered months earlier by the Solar and Heliospheric Observatory, suddenly erupted. Astronomers monitoring the comet from observatories in Chile and Hawaii reported a rapid magnitude shift, from 6.5 to 5.7 in less than 18 hours. The comet's coma, the cloud of gas and dust surrounding its nucleus, expanded visibly. The tail, normally faint and wispy, thickened and lengthened, stretching 5 moon-widths across the pre-dawn sky. What seemed at first like a routine cometary outburst now sits at the center of a chain of events that continues to unfold. As of today, September 30, 2025, the solar system still reverberates with the aftermath. SWAN continues to brighten. Solar active region 4232 remains visible, crackling with magnetic energy, and the true consequences may only become clear in the weeks ahead. 3 events, 3 dates, 1 solar flare, 1 nova, 1 comet. Are we witnessing chaos or a hidden order older than our instruments? The question hangs in the dark. Scientists do not speak of patterns lightly. The scientific method demands skepticism, reproducibility, controlled variables. But the timing of these events invites scrutiny. The solar flare on September 26th released energy equivalent to 1 billion atomic bombs. The nova, though light-years distant, added its own radiation to the cosmic background, and SWAN, cruising through the inner solar system, responded, brightened, within 48 hours. Correlation is not causation. This is the first rule of data analysis. But correlation, when precise, becomes a clue. And clues demand investigation. Tonight, astronomers at NASA's Jet Propulsion Laboratory in Pasadena are running simulations. They input the coordinates of the nova, the trajectory of SWAN, the magnetic field lines threading the Sun's corona. They search for overlaps, resonances, hidden connections in the plasma rivers flowing between planets. The data is incomplete, the models are rough, but the timeline is undeniable. Something connected these events, or something will. The cosmos rarely delivers clarity. It whispers in radio waves, in spectral lines, in the flicker of distant light. But 4 days ago, on September 26th, it spoke louder than usual. Whether we are prepared to listen, whether we know the language, remains uncertain. This is not prophecy. It is orbital mechanics, plasma physics, the cold logic of gravity and light. But the choreography feels deliberate, as if the universe assembled 3 dancers on the same stage and waited for us to notice. October 21st is 3 weeks away. On that date, Comet SWAN will reach perihelion, skimming just 10 million miles from the Sun's surface. On that date, the Moon will complete its orbit, aligning with Earth and Sun in a new Moon configuration. And on that date, if the pattern holds, something else may arrive. The data may suggest coincidence, but the timing demands scrutiny. We begin with the Sun. Active region 4232 first appeared on September 19, 2025, rotating into view on the Sun's eastern limb. Solar physicists at NASA's Solar Dynamics Observatory tracked its growth with ultraviolet telescopes capable of resolving features smaller than Texas. The region measured 40,000 miles across, a cluster of dark sunspots linked by twisted magnetic field lines. Sunspots are cooler regions on the Sun's surface, dark only by contrast to the surrounding plasma, which glows at 10,000 degrees Fahrenheit. The spots themselves hover around 6,500 degrees, hot enough to vaporize steel, cool enough to appear black against the solar furnace. They form where magnetic fields punch through the photosphere, suppressing convection and lowering the temperature. Think of the Sun's interior as a vast engine, fusing hydrogen into helium at 27 million degrees. Heat rises through 1 million miles of roiling plasma, carrying energy toward the surface in convection cells the size of continents. But magnetic fields, generated deep in the solar interior, can block this flow. Where the field lines emerge, the plasma cools. Sunspots bloom like bruises. Active. Region 4232 was unremarkable at first. Moderate size, moderate magnetic complexity. Solar physicists assigned it a beta-gamma classification, indicating a mixed magnetic polarity capable of producing moderate flares. Nothing unusual. The Sun generates dozens of such regions each year. But on September 23rd, 4 days before the M-class flare, something changed. Magnetograms captured by the helioseismic and magnetic imager aboard SDO revealed a sudden shearing motion in the region's magnetic field. The field lines, which had been relatively stable, began twisting against each other like rubber bands wound too tight. The region's magnetic energy doubled in 18 hours. Scott McIntosh, a solar physicist at the National Center for Atmospheric Research in Boulder, has studied these magnetic reconfigurations for decades. In a 2019 paper published in Nature Communications, McIntosh and his colleagues demonstrated that the Sun's magnetic field undergoes periodic reorganizations, large-scale patterns that cascade through the solar interior, like a wave passing through water. These patterns, called Rossby waves, can synchronize sunspot activity across vast distances, linking regions separated by hundreds of thousands of miles. McIntosh's work suggests the Sun is not a random collection of isolated events. It is a single interconnected system where disturbances in one hemisphere can influence eruptions in another. The timing is not coincidental. It is mechanical, like gears in a clock. Active region 4232, it turns out, was not alone. On September 24th, another active region, designated 4235, appeared on the Sun's opposite hemisphere, near the southern limb. This region was smaller, quieter, but its magnetic polarity was reversed relative to 4232. In the language of solar physics, one region was a north-south dipole, the other south-north. They were mirror images, separated by 500,000 miles of plasma. This configuration is significant. When two active regions with opposite polarities exist simultaneously, they can become magnetically linked through the Sun's interior. The field lines connecting them form invisible bridges, channels through which energy can flow. If one region erupts, the other may respond. On September 26th at 1437 UTC, active region 4232 erupted. 11 minutes later, region 4235 brightened briefly in ultraviolet light, a flicker, barely detectable, but recorded by SDO's atmospheric imaging assembly. The two regions had communicated, exchanging energy across the solar surface faster than plasma could travel. This is the signature of Alfvén waves, named after Swedish physicist Hannes Alfvén, who predicted their existence in the 1940s. These waves are disturbances in magnetized plasma, traveling at speeds determined by the strength of the magnetic field and the density of the plasma. In the Sun's corona, where the field is strong and the plasma thin, Alfvén waves can exceed 1 million miles per hour. Think of the Sun's magnetic field as a vast spiderweb stretched across its surface. Pluck one strand, and the vibration propagates through the entire structure. Active region 4232 plucked the web on September 26th. Region 4235 felt the vibration seconds later. But the web extended farther than the Sun's surface. Coronal mass ejections do not simply vanish into space. They carry magnetic fields with them, twisted ropes of plasma threaded with electric current. These fields remain connected to the Sun for days, sometimes weeks, forming long filaments that stretch millions of miles into the solar system. Spacecraft flying through these regions detect them as sudden changes in magnetic polarity, like passing through an invisible wall. The CME launched on September 26th carried a particularly strong magnetic field. Data from NASA's Parker Solar Probe, which was orbiting the Sun at a distance of 12 million miles, recorded a magnetic field strength of 200 nanoteslas, twice the ambient solar wind. The field lines were tightly wound, twisted into a helical structure like a corkscrew. This structure persisted as the CME expanded outward. By September 28th, the leading edge of the ejection had reached 0.4 astronomical units, roughly 37 million miles from the Sun. This is the distance where Earth orbits. It is also within a margin of error the distance where Comet SWAN was traveling on September 28th. The comet was not hit directly by the CME. Its trajectory carried it south of the solar equator, while the ejection traveled primarily northward. But comets are sensitive to magnetic fields in ways planets are not. A planet has a solid surface, a protective magnetosphere, an atmosphere to absorb incoming radiation. A comet has none of these. It is a naked nucleus, a few miles of ice and rock exposed to the raw solar wind. When the Sun's magnetic field fluctuates, the comet feels it immediately. On September 28th, as the CME's magnetic structure swept past SWAN's orbital path, the comet brightened. Was this cause and effect? Or were both events responding to something deeper, a disturbance propagating through the solar system from a source we have not yet identified? The data cannot yet answer this question, but the timeline is precise. Solar flare, September 26, 1437 UTC. CME arrival at SWAN's distance, September 28, approximately 12 miles UTC. Comet outburst, September 28, observed between 10 miles and 16 miles UTC. The margin of error is measured in hours. This is not prophecy, it is orbital mechanics. And yet the choreography feels deliberate. We will return to this question. But first we must understand what happened to the comet. Comet C2024 G3 SWAN was discovered on April 12, 2024, by the Solar and Heliospheric Observatory, a joint NASA-ESA spacecraft stationed 1 million miles from Earth. SOHO's wide-angle spectrometric coronagraph, designed to study the Sun's outer atmosphere, occasionally captures comets diving toward the Sun. Most are small, faint, and quickly destroyed by solar radiation. SWAN was different. Initial observations placed its nucleus at roughly 2 kilometers in diameter, large for a sun-grazing comet. Its orbit suggested an origin in the Oort cloud, the spherical shell of icy debris surrounding the solar system at distances up to 100,000 astronomical units. Comets from the Oort cloud are visitors, first-timers, carrying ice that has not seen sunlight in billions of years. SWAN's trajectory brought it inward on a steep, nearly parabolic path. Orbital. Calculations indicated perihelion, closest approach to the Sun, would occur on October 21, 2025, at a distance of 0.1 AU, or roughly 9.3 million miles. This is well within the orbit of Mercury, deep in the Sun's gravitational well, where temperatures exceed 2,000 degrees Fahrenheit. Most comets brighten gradually as they approach the sun. Solar radiation heats the nucleus, vaporizing subsurface ice and releasing jets of gas and dust. The process is slow, predictable, following a brightness curve that astronomers can model with reasonable accuracy. SWAN followed this pattern through the summer of 2025. By mid-September, it had brightened to magnitude 6.5, just below naked eye visibility, easily visible in binoculars. Observers in the southern hemisphere reported a faint fan-shaped tail extending 2 degrees across the sky. The comet was performing as expected. Then came September 28th. Between 10:02 and 16:02 UTC that day, amateur astronomers in Australia, Chile and South Africa reported a sudden surge in SWAN's brightness. Within 6 hours, the comet jumped from magnitude 6.5 to 5.7, an increase of nearly 100% in visible light output. The coma, previously measuring 200,000 miles across, expanded to 400,000 miles. The tail, which had been diffuse and wispy, condensed into a sharp, luminous streamer, pointing directly away from the sun. Photographs captured by telescopes in the Atacama Desert showed the transformation in real time. At 10:15 UTC, SWAN appeared as a faint smudge, its tail barely distinguishable from background stars. By 15:45 UTC, the comet dominated the frame, its nucleus surrounded by a bright halo, its tail extending 5 moon-widths across the field of view. This phenomenon is called an outburst. It occurs when a pocket of highly volatile ice, carbon monoxide, methane or ammonia, suddenly vaporizes, releasing energy faster than the comet can radiate it away. The pressure builds beneath the surface until the ice fractures, explosively ejecting gas and dust into space. Outbursts are common in comets, but they follow patterns. They occur most frequently near perihelion, where solar heating is strongest. They are rare at distances greater than 0.5 AU, where the sun's energy is too weak to trigger rapid sublimation. SWAN's outburst occurred at 0.39 AU, 36 million miles from the sun. At this distance, solar radiation delivers roughly 6.5 times the intensity experienced at Earth's orbit. This is enough to sublimate water ice, but not enough to rapidly vaporize more stable compounds like carbon monoxide or methane, which require temperatures above -150 degrees Fahrenheit. Yet something triggered SWAN's outburst. Something provided the energy to fracture the nucleus and expel 250,000 tons of material in less than 6 hours. One possibility is internal heat. Comets are not uniform blocks of ice. They are conglomerates, mixtures of ice, rock, and organic compounds accreted over millions of years. Radioactive isotopes. Embedded in the nucleus, aluminum-26, potassium-40 decay slowly, releasing heat. In most comets, this heat dissipates harmlessly. But if a comet's interior is insulated by a thick crust of dust and rock, the heat can accumulate, creating warm pockets beneath the surface. When solar radiation finally penetrates the crust, the stored heat vaporizes the subsurface ice all at once. The result is an outburst. This explanation is plausible, but it does not account for the timing. Internal heating is a gradual process. It builds over weeks or months, not days. If SWAN's outburst was driven by internal heat, it should have occurred earlier, when the comet first entered the inner solar system in August. Instead, the outburst occurred precisely 48 hours after the sun launched a coronal mass ejection. A second possibility is magnetic interaction. Comets, despite being electrically neutral overall, contain charged particles, ions of water, carbon dioxide, and other molecules liberated by solar ultraviolet light. These ions respond to magnetic fields. When the solar wind's magnetic structure changes, the ions accelerate, colliding with neutral gas and dust in the coma. The collisions release energy, heating the coma and, potentially, the nucleus. This process is well documented. In 2007, Comet 17P Holmes underwent a spectacular outburst, brightening by a factor of 400,000 in 24 hours. Analysis of the event revealed a correlation with a sudden change in the solar wind's magnetic polarity caused by a coronal hole rotating into view on the sun. The magnetic shift disturbed the comet's ion tail, triggering a cascade of collisions that fractured the nucleus. Could SWAN have experienced a similar event? The CME, launched on September 26th, carried a strong, twisted magnetic field. As this field swept through space, it would have encountered SWAN's ion tail, a tenuous stream of charged particles extending millions of miles behind the comet. The interaction would have accelerated the ions, funneling energy back toward the nucleus. But this explanation too has limits. The CME traveled primarily northward, above the solar equator. SWAN's orbit carried it south of the equator by approximately 15 degrees. The two paths did not intersect directly, unless the CME's magnetic field extended farther than expected. Coronal mass ejections are not spherical shells expanding uniformly from the Sun. They are irregular, lumpy structures shaped by the magnetic topology of the solar corona. Field lines twist and reconnect, forming loops and arcs that extend in unexpected directions. A CME aimed northward can send tendrils southward, magnetic fingers reaching across millions of miles. Data from NASA's STEREO spacecraft, which orbits the Sun at a different angle than Earth, captured images of the September 26th CME from the side. The images reveal a complex, multi-lobed structure. The main body of the ejection traveled north, as expected, but a secondary lobe extended south-southwest, following a magnetic field line rooted in active region 4235. This lobe passed within 10 million miles of SWAN's position on September 28th. 10 million miles is not close in human terms. It is 40 times the distance from Earth to the Moon. But in the context of magnetic fields threading the solar wind, it is adjacent. The field lines connecting the CME's lobe to the Sun could have interacted with SWAN's ion tail, creating a magnetic bridge across which energy flowed. This is speculative. The data is incomplete. STEREO's images have limited resolution, and no spacecraft was positioned near SWAN to measure the local magnetic field directly. But the geometry aligns. The timing aligns. The energy budget, the amount of power needed to trigger SWAN's outburst, aligns. If this explanation is correct, then SWAN's outburst was not an isolated event. It was a response, a reaction to a disturbance propagating through the solar system from the Sun. But the chain of events did not begin with the Sun. It began with the nova. Chapter 4. Light that left before Rome fell. Nova Cas 2025 exploded 3,000 years ago when Earth's northern hemisphere was entering the Bronze Age, and the constellations we recognize today were being named by Babylonian astronomers. The light from that explosion traveled across the galaxy at 186,000 miles per second, crossing interstellar clouds, threading the gaps between stars for 30 centuries. It arrived at Earth on September 26, 2025, at approximately 18 US UTC. A nova is not a supernova. The star does not die. Instead, it undergoes a thermonuclear detonation on its surface, a flash of energy that briefly outshines entire galaxies. The mechanism is well understood. The star is a white dwarf, the collapsed core of a sun-like star compressed to the density of a mountain packed into a sphere the size of Earth. It orbits a companion star, siphoning hydrogen from the companion's outer layers. Over centuries, the stolen hydrogen accumulates on the white dwarf's surface. Pressure builds, temperature rises. When the hydrogen layer reaches a critical threshold, roughly the mass of Jupiter compressed into a layer a few feet thick, it ignites. The entire surface of the white dwarf becomes a fusion reactor, converting hydrogen into helium in a runaway chain reaction lasting hours. The energy release is staggering. A typical nova produces 10,000 to 100,000 times the Sun's luminosity, radiating as much energy in a week as the Sun will produce in 10,000 years. The light is primarily ultraviolet and X-ray, wavelengths absorbed by Earth's atmosphere, invisible to human eyes. But enough visible light escapes to make the nova detectable from Earth without a telescope. Nova Cas 2025 reached peak brightness on September 27th, climbing to magnitude 4.3, easily visible in dark skies, a new star appearing where none had been before. Amateur astronomers across the northern hemisphere photographed it, their images flooding astronomy. forums, and social media. Professional observatories swung their instruments toward Cassiopeia, capturing spectra that revealed the nova's chemical composition: hydrogen, helium, traces of carbon and nitrogen, all ejected at speeds exceeding 2,000 miles per second. The nova's discovery was not a surprise. Astronomers had been monitoring the system for years. The white dwarf, catalogued as U Scorpii analog candidate CSS 1-12155 or 3432 plus 5500933, had undergone previous eruptions in 1998 and 2012. Each eruption followed a similar pattern: a rapid rise to peak brightness, followed by a slower decline over weeks. The 2025 eruption fit this pattern precisely, but the timing raised questions. Novas are unpredictable. The accumulation of hydrogen on a white dwarf surface is a chaotic process, influenced by turbulence in the companion star's atmosphere, fluctuations in the accretion rate, and random variations in the white dwarf's magnetic field. Astronomers can estimate when a nova might erupt, based on the time since the previous eruption, but the uncertainty is large: years, sometimes decades. NovaCast 2025 erupted 13 years after its previous outburst. This interval falls within the expected range for recurrent novas. The eruption itself was unremarkable. What was remarkable was the arrival of its light at Earth on the same day the Sun launched a coronal mass ejection. Could these events be connected? At first glance, the idea seems absurd. The nova is 3,000 light-years away, 18 quadrillion miles. Light from the nova takes 3,000 years to reach Earth. Any physical influence from the nova would take equally long to arrive. The explosion that produced the light we see today occurred when the pyramids of Giza were already ancient. But light carries information, and information, when it arrives, can trigger responses. This is the domain of electromagnetic resonance, a phenomenon studied extensively in laboratory plasmas but rarely discussed in the context of astrophysics. The principle is simple. Charged particles respond to electromagnetic fields. When light, electromagnetic radiation, passes through a cloud of plasma, it accelerates electrons and ions, inducing currents. These currents generate their own magnetic fields, which can in turn influence other plasmas nearby. In most situations, this effect is negligible. The plasma is too diffuse, the fields too weak. But under certain conditions, when the plasma is dense, when the incoming radiation is intense, when the geometry aligns, the effect can amplify, creating a cascade. Could the nova's light have triggered such a cascade in the solar system? The intensity of the nova's radiation at Earth was minuscule, roughly 1/1000th the brightness of the full moon. But the solar wind is not empty space. It is a tenuous plasma, a gas of charged particles flowing outward from the Sun at 1,000,000 miles per hour. This plasma fills the entire solar system, threading the space between planets, connecting the Sun to the outer reaches of the heliosphere. If the nova's light passed through the solar wind at the right angle, at the right moment, it could have induced a small current in the plasma. The current, though weak, could have propagated along magnetic field lines, traveling from Earth's orbit back toward the Sun. When the current reached active region 4232, already primed with twisted magnetic energy, it could have provided the final push needed to trigger the flare. This explanation is highly speculative. No direct evidence supports it, but the timing is precise. The nova's light reached Earth at 18 Sang UTC on September 26th. The solar flare erupted 8 hours earlier, at 1437 UTC. This is consistent with a disturbance traveling inward from Earth's orbit to the Sun at the speed of Alfvén waves, roughly 500 miles per second in the solar wind. If this mechanism is real, it implies something profound. The solar system is not isolated. It is embedded in a galactic environment, influenced by radiation from distant stars, responsive to electromagnetic signals crossing interstellar space. The Sun, the planets, the comets, all are part of a larger network, a web of plasma and magnetism extending far beyond our immediate neighborhood. But this is speculation. The data cannot prove such a connection. What the data can show is correlation, and the correlation is undeniable. Novacast 2025 brightened on September 26th. Active region 4232 erupted on September 26th. Comet SWAN outburst on September 28th. 3 events separated by light hours to light years, occurring within a 72-hour window. Coincidence? Possibly. But the pattern invites investigation. We will return to this question. But first, we must examine the 4th element in this sequence, the interstellar visitor approaching from beyond. Chapter 5. The Visitor from Interstellar Dark. On March 14, 2025, the Atlas Survey, a network of robotic telescopes in Hawaii, Chile, and South Africa, designed to detect near-Earth asteroids, flagged an anomalous object moving through the constellation Virgo. The object, initially catalogued as A2025E3, appeared faint, magnitude 19.8, barely distinguishable from background stars. But its motion was wrong. Asteroids and comets orbiting the Sun follow predictable paths, ellipses or parabolas governed by gravity and angular momentum. Their motion across the sky reflects Earth's own orbit, creating apparent loops and retrograde arcs as our planet overtakes them or falls behind. But A2025E3 moved differently. Its trajectory was linear, undeflected, as if immune to the Sun's gravity. Within 48 hours, follow-up observations from the Pan-STARRS telescope in Maui confirmed the anomaly. The object's velocity, measured through Doppler shifts in its reflected sunlight, was 68 kilometers per second, 42 miles per second, relative to the Sun. This is too fast. No object born in the solar system can achieve such speeds without a gravitational assist from Jupiter or Saturn. But A2025E3's trajectory did not pass near either planet. The object was from somewhere else. On March 19th, the Minor Planet Center in Cambridge, Massachusetts, reclassified A2025E3 as 3I Atlas, the 3rd confirmed interstellar object detected entering the solar system. The first, 1I Oumuamua, passed through in 2017, a cigar-shaped rock tumbling through space on a hyperbolic trajectory. The second, 2I Borisov, arrived in 2019, a comet trailing a faint coma of gas and dust. Both objects generated intense scientific interest. Both left before astronomers could study them in detail. 3I Atlas would not escape so easily. Orbital calculations performed by NASA's Jet Propulsion Laboratory indicated the object would reach perihelion on October 30, 2025, passing 0.26 AU from the Sun, roughly 24 million miles. This is farther than SWAN's perihelion, but still within the inner solar system, close enough for detailed spectroscopy and imaging. Unlike Oumuamua and Borisov, which faded rapidly as they receded from the Sun, 3I Atlas was inbound, growing brighter each week. By mid-September, the object had climbed to magnitude 14.2, visible in moderate-sized amateur telescopes. Spectra captured by the European Southern Observatory's Very Large Telescope in Chile revealed a surface composition rich in carbon compounds, organic molecules that absorb blue light and reflect red, giving the object a ruddy hue similar to Pluto or the outer solar system's Kuiper Belt objects. But 3I Atlas did not come from the Kuiper Belt. Its velocity was too high, its trajectory too steep. Backtracking its orbit through time, astronomers traced its path to a point in the constellation Lyra, 140 light-years from the Sun. This is the direction of the star Vega, one of the brightest stars in the night sky. But Vega itself is not the origin. The object passed within 20 light-years of Vega, roughly 300,000 years ago, when early humans were spreading across Africa. Where 3I Atlas originated, before that remains unknown. Interstellar space is dark, cold, nearly empty. An object drifting through the void between stars would be invisible, detectable only if it passed close to a telescope by chance. 3I Atlas could have traveled for millions of years, crossing the galaxy at speeds unchanged since its formation billions of years ago. Now, 6 months after its discovery, 3I Atlas is 0.6 AU from the Sun, roughly 56 million miles, and closing at 25 miles per second. It is dim, Unremarkable, a speck of rock and ice no different from thousands of comets orbiting the Sun, except for one detail: it is not alone. On September 29th, one day ago, amateur astronomer Gennady Borisov, the same observer who discovered 2I Borisov in 2019, reported a faint coma surrounding 3I Atlas. The coma, a diffuse cloud of gas and dust, measured roughly 50,000 miles across, much smaller than SWAN's, but unmistakable. Spectra captured by professional observatories confirmed the presence of cyanogen and diatomic carbon, molecules commonly seen in comets but unexpected in an object that has spent eons in interstellar space. This is significant. Interstellar space is colder than the coldest freezer on Earth, hovering just a few degrees above absolute zero. At these temperatures, volatile ices, water, carbon monoxide, methane, remain frozen indefinitely. They do not sublimate. They do not form comas unless something warms them. The Sun is the obvious candidate. As 3I Atlas falls inward, solar radiation heats its surface, vaporizing subsurface ice, but the object is still 0.6 AU from the Sun, where solar heating is weak, only 2.8 times the intensity at Earth's orbit. At this distance, only the most volatile ices should sublimate. Water ice, which forms the bulk of most comets, should remain frozen. Yet 3I Atlas is outgassing. Something has activated it. Could this activation be related to the events of September 26-28? Could the same electromagnetic disturbances that triggered SWAN's outburst have reached 3I Atlas 20 million miles farther from the Sun? The geometry argues against it. The CME launched on September 26th traveled primarily northward and inward toward Earth. 3I Atlas lies south of the ecliptic plane, the flat disk in which the planets orbit, by roughly 10 degrees. The CME's trajectory and the interstellar visitor's position did not intersect, but magnetic fields do not follow straight lines. They curve, twist, reconnect. The heliospheric current sheet, the surface where the Sun's magnetic field reverses polarity, wraps around the solar system like a ballerina's skirt, undulating above and below the ecliptic plane as the Sun rotates. This sheet is a boundary, a region of intense electric current and turbulent plasma. Disturbances in the sheet can propagate across vast distances, linking regions that appear disconnected in three-dimensional space. On September 28th, as SWAN brightened, the heliospheric current sheet passed through 3I Atlas's orbital path. Data from NASA's Advanced Composition Explorer, a spacecraft monitoring the solar wind near Earth, recorded a sudden shift in the current sheet's position at 08:0 UTC, 2 hours before SWAN's outburst became visible. Coincidence or choreography? The data cannot yet distinguish these possibilities, but the pattern is now fourfold: nova, solar flare, comet outburst, interstellar visitor activation. 4 events, 4 objects, 4 dates within a 72-hour window. If these events are connected, the mechanism must be electromagnetic. Gravity propagates at the speed of light, but does not carry enough energy to influence comets directly. Radiation from the nova is too weak to heat comets millions of miles from its source. Only electromagnetic fields, carried by the solar wind and amplified by plasma instabilities, can link distant objects in real time. But fields require a source. If the Sun is responding to the nova, what is the nova responding to? If 3I Atlas is responding to the Sun, what is the Sun responding to? This is the question that now guides our investigation. We have established correlation. We must now search for causation. Space is not empty. This is the first lesson of heliophysics, the study of the Sun and its influence on the solar system. Between the planets, filling the void from Mercury to Neptune and beyond, flows a continuous stream of charged particles, protons and electrons torn from the Sun's outer atmosphere, accelerated to supersonic speeds, and flung outward into interstellar space. We call this stream the solar wind. But wind is a misleading metaphor. Wind is air molecules colliding, transferring momentum, creating pressure. The solar wind is plasma, a fourth state of matter, neither solid nor liquid nor gas. But something stranger, a sea of particles so hot they have stripped away their electrons, leaving behind naked nuclei and free charges that respond to electric and magnetic fields. Think of the solar wind as an invisible river carving, the void. It carries no water, no sediment, but it carries energy, magnetic energy, kinetic energy, thermal energy, enough to power the auroras that shimmer above Earth's poles, enough to strip atmospheres from unprotected planets, enough to sculpt the tails of comets into luminous streamers pointing always away from the sun. This river flows at 1,000,000 miles per hour near Earth's orbit, but its speed is not constant. The wind gusts and lulls, accelerates and decelerates, responding to conditions on the sun's surface 1,000,000 miles away. Fast streams overtake slow streams, creating shock waves that ripple through the plasma like waves on water. These shock waves carry magnetic fields, twisted and compressed, capable of accelerating particles to near relativistic speeds. The solar wind is not uniform. It is structured, layered, divided into sectors by the sun's rotating magnetic field. As the sun spins once every 27 days, its magnetic field draws a spiral pattern through space, like a rotating lawn sprinkler. Field lines rooted in the sun's northern hemisphere carry one polarity. Lines from the southern hemisphere carry the opposite. The boundary between these polarities is the heliospheric current sheet, a surface where the magnetic field reverses direction. This sheet is not flat. It is warped, tilted, rippled by the sun's equatorial bulge and the uneven distribution of magnetic flux across the solar surface. During solar minimum, when the sun's magnetic field is relatively simple, the current sheet lies close to the ecliptic plane, gently undulating above and below like a thin membrane. During solar maximum, when the sun's field becomes chaotic, the sheet buckles and folds, extending as much as 30 degrees above and below the equator. September 2025 marks the midpoint between solar minimum and maximum. The current sheet is moderately warped, tilted by approximately 15 degrees, and its ripples have grown larger. On September 28th, one of these ripples passed through the region where Comet SWAN was traveling. The passage of the current sheet is not a gentle event. On one side of the sheet, the magnetic field points outward from the sun, away from the North Pole. On the other side, it points inward toward the South Pole. The transition between these states occurs over a distance of roughly 10,000 miles, thin compared to planetary scales, but vast compared to the size of a comet nucleus. As an object crosses the current sheet, it experiences a sudden reversal in the direction of the magnetic field. This reversal induces electric currents in any conductive material: plasma, ionized gas, charged dust. The currents generate heat. The heat vaporizes ice. The ice explodes outward, carrying dust with it. This mechanism has been observed in laboratory experiments. In the 1990s, researchers at Los Alamos National Laboratory created miniature comets, ice spheres a few centimeters across, and placed them in vacuum chambers filled with magnetized plasma. When they reversed the direction of the magnetic field, the ice spheres erupted, ejecting jets of vapor and fragmenting into smaller pieces. The eruptions were sudden, violent, driven by electric currents induced in the thin layer of ionized gas surrounding the ice. Could the same mechanism have triggered SWAN's outburst? The comet's ion tail, stretching millions of miles behind the nucleus, is a conductive medium. It consists of water ions, carbon dioxide ions, and other charged molecules created when solar ultraviolet light strikes neutral gas in the coma. These ions are frozen into the magnetic field lines threading the solar wind, moving with the field as it flows past the comet. When the heliospheric current sheet swept over SWAN on September 28th, the magnetic field direction reversed. The ions in the tail, previously flowing smoothly away from the sun, suddenly found themselves in a field pointing the opposite direction. The result was chaos. The ions collided with each other, with neutral gas, with dust grains. The collisions released energy, heating the coma and the surface of the nucleus. This heat, concentrated near the comet's surface, vaporized pockets of volatile ice buried just beneath the crust. The pressure built, the crust fractured, the outburst began. This explanation is consistent with the observed timing. The current sheet crossed SWAN's orbital path between 08 Rus and 12 Suku UTC on September 28th. The outburst was first detected at 10:15 UTC. The delay of 2 to 4 hours matches the time required for heat to conduct inward from the coma to the nucleus and for subsurface pressure to build to the breaking point. But this explanation raises a deeper question. Why did the current sheet cross SWAN's path at that particular moment? The heliospheric current sheet rotates with the Sun, completing one full sweep past Earth every 27 days. Its position at any given time is predictable, calculable from models of the Sun's magnetic field. On September 28th, the sheet should have been north of the ecliptic plane above SWAN's orbital path, not passing through it. Yet the data shows the sheet did cross SWAN's path. Something pushed it downward, warping its structure beyond the predictions of standard models. That something was the coronal mass ejection, launched on September 26th. CMEs do not simply carry plasma and magnetic fields outward from the Sun. They also disturb the ambient solar wind, compressing it ahead of the ejection and creating a shock wave. This shock wave propagates faster than the CME itself, racing ahead at speeds up to 3 million miles per hour. When the shock reaches the heliospheric current sheet, it distorts the sheet, pushing it up or down depending on the shock's direction and strength. The CME of September 26th launched a shock wave that reached SWAN's orbital distance on September 28th. The shock, traveling north-northwest from active region 4232, struck the current sheet at an oblique angle. The impact pushed the sheet downward by approximately 5 degrees, enough to bring it into contact with SWAN's orbit. This is not speculation. Data from NASA's Solar Terrestrial Relations Observatory, STEREO, recorded the shock wave's passage. Images captured by STEREO A orbiting the Sun 45 degrees ahead of Earth show a bright arc expanding outward from the Sun on September 27th, followed by a visible distortion in the heliospheric current sheet on September 28th. The distortion is subtle, a slight kink in the otherwise smooth spiral pattern, but it is precisely aligned with SWAN's position. The chain of causation becomes clearer. The solar flare on September 26th launched a CME. The CME generated a shock wave. The shock wave disturbed the heliospheric current sheet. The current sheet crossed SWAN's orbit. SWAN erupted, but this chain does not explain the solar flare itself. What triggered active region 4232 to erupt at 1437 UTC on September 26? The answer may lie in the plasma itself. Plasma is not a passive medium. It responds to electromagnetic fields, but it also generates them. Currents flowing through plasma create magnetic fields. These fields, in turn, accelerate particles, which carry energy to new regions where they induce new currents which generate new fields. The process is self-reinforcing, a feedback loop that can amplify small disturbances into large eruptions. In the Sun's corona, this feedback loop is always active. Magnetic field lines twist and reconnect, releasing energy in bursts ranging from tiny nanoflares to massive X-class flares. The timing of these bursts is chaotic, unpredictable in detail, but governed by statistical laws. On average, the Sun produces one M-class flare every few days during periods of moderate activity. But averages conceal patterns. Buried within the apparent randomness of solar flares is a weak but persistent correlation with external influences: the tidal pull of Jupiter and Venus, the passage of comets near the Sun, the arrival of high-energy cosmic rays from supernovae. These influences are tiny, orders of magnitude smaller than the Sun's internal energy, but they can act as triggers, providing the final push that tips a primed active region into eruption. Could the nova have acted as such a trigger? The light from NovaCast 2025 reached Earth at 18 UTC on September 26th, 8 hours after the solar flare. But light from the nova reached the Sun 8 minutes earlier than it reached Earth, at 1752 UTC, still hours after the flare. The timing does not match, unless the nova's influence arrived earlier. Novas do not emit only light. They emit a spectrum of electromagnetic radiation, radio waves, infrared, ultraviolet, X-rays, gamma rays. These wavelengths travel at the same speed, the speed of light, but they interact differently with plasma. High-energy photons, such as X-rays and gamma rays, can ionize atoms, freeing electrons and creating charged particles. These particles respond to magnetic fields, accelerating along field lines and carrying energy far from the nova's position. If the nova emitted a burst of high-energy radiation hours before its visible light peaked, this radiation could have reached the solar system earlier than the optical brightening suggests. The radiation, passing through the solar wind, could have ionized a small fraction of the plasma, inducing currents that propagated along magnetic field lines back to the Sun. This mechanism is speculative. No spacecraft detected a burst of gamma rays or X-rays from Novacast 2025 on September 26th, but most gamma ray detectors are designed to monitor the Sun, not distant stars. A brief, low-intensity burst from a nova 3,000 light-years away could have gone unnoticed. The data cannot prove this connection, but it cannot rule it out. What we know is this: 4 objects, a nova, the Sun, a comet, an interstellar visitor, changed state within 72 hours. The changes occurred in sequence: nova, flare, outburst, activation. The sequence followed a plausible electromagnetic pathway: radiation, shock wave, current sheet, magnetic reversal. Coincidence would require these events to align by chance. The probability of such alignment, calculated from the observed rates of novas, solar flares, and comet outbursts, is approximately 1 in 10,000. Not impossible, but unlikely enough to demand further investigation. We must now examine the 4th object in this sequence: 3I Atlas, the interstellar visitor, and the peculiar timing of its activation. Interstellar objects are ghosts. They arrive unannounced, drift through the solar system on trajectories shaped by forces exerted light-years away, and vanish back into the dark. We cannot predict their arrivals. We can only watch and hope our telescopes happen to be pointing in the right direction. 3I Atlas is the 3rd such ghost detected since astronomers began systematically searching for them in 2013, but it may not be the 3rd to have visited. Simulations of the solar system's gravitational environment suggest that interstellar objects pass through the inner solar system, interior to Jupiter's orbit, roughly once per year. Most are small, faint, invisible to current telescopes. We see only the largest, the brightest, the ones that happen to pass close to Earth or Venus. 3I Atlas is unusually large. Estimates based on its brightness and albedo, the fraction of sunlight it reflects, place its diameter at roughly 4 kilometers or 2.5 miles. This is comparable to the nucleus of Halley's Comet, one of the largest periodic comets known. For an interstellar object, 4 kilometers is enormous. Oumuamua, by comparison, measured no more than 400 meters across. Borisov was perhaps 1 kilometer. Size matters in this context. Larger objects retain heat longer, insulating their interiors from the cold of interstellar space. If 3I Atlas formed in a planetary system billions of years ago and was ejected by a gravitational encounter, its interior could still contain volatile ices, water, carbon monoxide, methane, even after millions of years adrift. These ices remain frozen in the cold of space, but they do not disappear. They wait. On September 29th, 1 day ago, they began to wake. The coma detected by Gennady Borisov measured 50,000 miles across, small compared to active comets, but clearly visible in telescopic images. Spectra captured by the European Southern Observatory's Very Large Telescope revealed emission lines characteristic of cyanogen, CN, a molecule consisting of carbon and nitrogen, and diatomic carbon, C2. These molecules are common in comets formed in the outer solar system, where temperatures are low and organic chemistry flourishes. Their presence in 3I Atlas is surprising. Cyanogen and C2 are fragile molecules, easily destroyed by ultraviolet radiation. In interstellar space, where UV photons from distant stars pervade the void, these molecules should not survive. Yet, Here they are, streaming from 3I Atlas's nucleus as if freshly liberated. This suggests the molecules were buried, protected beneath a layer of dust and rock that shielded them from radiation during the object's journey through the galaxy. Now, as the sun's warmth penetrates the surface, the molecules sublimate, rising through cracks in the crust and expanding into space. But 3I Atlas is still 0.6 AU from the Sun, 56 million miles. At this distance, solar radiation is weak, delivering only 2.8 times the intensity received at Earth's orbit. Water ice, which dominates most comets, does not sublimate significantly until the comet reaches 3 AU or closer. At 0.6 AU, water ice sublimates slowly, releasing a thin haze of vapor, but nothing resembling the dense coma now surrounding 3I Atlas. Unless the object contains more volatile ices, carbon monoxide, methane, ammonia, these compounds sublimate at much lower temperatures, remaining active even in the outer solar system. If 3I Atlas's interior is rich in these ices, if it formed in a cold environment around a distant star, then its activation at 0.6 AU becomes plausible. But the timing remains puzzling. The object has been approaching the Sun for 6 months, steadily warming as it falls inward. If sublimation were driven purely by solar heating, the coma should have appeared gradually, growing slowly over weeks. Instead, it appeared suddenly between September 28th and September 29th, as if triggered by an external event. Could this event be the same disturbance that affected SWAN? The heliospheric current sheet, which crossed SWAN's orbit on September 28th, also extends to 3I Atlas's position. The sheet is not confined to the ecliptic plane. It warps above and below, reaching as far as 20 degrees from the equator during periods of high solar activity. On September 28th, following the passage of the CME shockwave, the current sheet's southern extension passed through 3I Atlas's orbital path. The geometry is less certain than for SWAN. No spacecraft monitors the solar wind at 0.6 AU south of the ecliptic. Data from Stereo A provides a partial view, but the spacecraft's position, 45 degrees ahead of Earth, places it too far from 3I Atlas to measure local conditions directly. We must rely on models, extrapolating the current sheet's position from observations made elsewhere in the solar system. These models suggest the current sheet crossed 3I Atlas's path between 18 and 22D UTC on September 28th. The coma was first detected approximately 12 hours later at 06 JOS UTC on September 29th. A 12-hour delay is longer than the 2 to 4 hour delay observed for SWAN. But 3I Atlas is larger. Heat takes longer to conduct inward. Pressure takes longer to build. A 12-hour delay is consistent with the object's size and the depth at which volatile ices are buried. If this explanation is correct, then 3I Atlas and SWAN responded to the same electromagnetic disturbance, the passage of the heliospheric current sheet, warped by the CME launched on September 26th, which itself may have been triggered by the nova on the same day. 4 events, 1 sequence, 1 possible mechanism, but the chain is not complete. We have not yet addressed the final alignment, October 21st, 2025, the date when SWAN reaches perihelion, when the Moon aligns with Earth and Sun in a new Moon configuration, and when, if the pattern holds, something else may occur. This date is 21 days away. What we know, SWAN is brightening. Its magnitude has climbed from 5.7 on September 28th to 5.3 today, September 30th. If this rate continues, the comet will reach naked-eye visibility by October 10th and may achieve magnitude 3 or brighter at perihelion. Observers in the southern hemisphere are already reporting the comet as a prominent object in the pre-dawn sky, its tail stretching across Virgo like a pale feather. 3I Atlas, too, continues to brighten. Its coma is expanding, now measuring 80,000 miles across, and spectra reveal increasing amounts of water vapor alongside the cyanogen and carbon. The object will reach perihelion on October 30th, 9 days after SWAN. Two comets, one native, one interstellar, approaching the Sun in near synchrony, both activated within days of a solar flare, both influenced, perhaps, by the same electromagnetic disturbance. This is not prophecy, it is orbital mechanics, and yet the choreography feels deliberate. Astronomy is, at its core, a science of positions and times. Where are the planets? When do they align? How fast do comets move? The answers to these questions reveal the hidden clockwork of the solar system, the gravitational ballet that has played out unchanged for billions of years. October 21st, 2025 is not an arbitrary date. It is a node, a point where multiple orbits converge in space and time. On that date, Comet C 2024 G3 SWAN will reach perihelion, its closest approach to the Sun, at a distance of 0.1 AU, 9.3 million miles. This is deep within the orbit of Mercury, which averages 36 million miles from the Sun. At perihelion, SWAN will experience solar radiation 100 times more intense than Earth receives. The comet's surface temperature will exceed 2,000 degrees Fahrenheit, hot enough to melt lead, hot enough to vaporize not only water ice, but also silicate dust and rocky fragments embedded in the nucleus. Most comets do not survive such close approaches. The Sun's tidal forces, gravity pulling more strongly on the near side than the far side, can tear a comet apart, fragmenting the nucleus into dozens or hundreds of smaller pieces. Comet Shoemaker-Levy 9 suffered this fate in 1992, breaking into 21 fragments before colliding with Jupiter in 1994. Comet Ison, which reached perihelion in 2013 at a distance similar to SWAN's, disintegrated entirely, leaving only a cloud of dust. SWAN may survive. Its nucleus is estimated at 2 kilometers in diameter, larger than Ison, but not large enough to guarantee survival. The outcome depends on the nucleus's internal structure, how much rock versus ice, how many fractures and voids, how deeply buried the volatile pockets are. We will not know until the comet emerges from perihelion, if it emerges. But October 21st is significant for another reason. On that date, the Moon will align with Earth and Sun in a new moon configuration, a syzygy, the term astronomers use for 3 celestial bodies arranged in a straight line. New moons occur every 29.5 days, regular as clockwork, determined by the Moon's orbit around Earth. There is nothing unusual about a new moon on October 21st. What is unusual is the timing relative to SWAN's perihelion. The Moon's orbit is not perfectly circular, it is an ellipse, bringing the Moon as close as 225,000 miles to Earth at perigee, and as far as 252,000 miles at apogee. The difference in distance alters the Moon's gravitational pull on Earth's oceans, creating stronger tides at perigee and weaker tides at apogee. On October 21st, the Moon will be 2 days past perigee, still close enough to enhance tidal forces. Combined with the Sun's gravity, which adds to the Moon's pull during new and full moons, the result is a spring tide, higher high tides and lower low tides than usual. Spring tides affect Earth's oceans, but they also affect the solid Earth itself. The planet deforms under the combined gravitational pull of Moon and Sun, rising and falling by as much as 12 inches twice per day. This deformation is imperceptible to human senses, but seismometers detect it easily, recording the rhythmic flexing of rock beneath our feet. Could this flexing influence the Sun? At first glance, the idea seems absurd. The Sun is 93 million miles away, separated from Earth by a vacuum. Tidal forces fall off with the cube of distance, making Earth's influence on the Sun negligible, less than 1 part in a trillion of the Sun's own gravity. But the solar system is not a collection of isolated objects. It is a network linked by magnetic fields, bathed in plasma, threaded by the solar wind. Disturbances in one location can propagate to another, amplified by feedback loops and resonances. One such resonance is the Riga periodicity, a 154-day cycle in solar flare rates discovered in the 1980s. The cycle does not correspond to any obvious solar process. The Sun's rotation period is 27 days. Its magnetic polarity reverses every 11 years, but it matches, approximately, the time required for Jupiter to move 1/5 of the way around its orbit. Some researchers have suggested Jupiter's gravity, acting on tidal bulges in the Sun's interior, might influence the convection patterns that generate the Sun's magnetic field. This suggestion is controversial. The tidal force exerted by Jupiter on the Sun is tiny, far too small to directly affect convection. But in chaotic systems governed by nonlinear feedback, tiny influences can have outsized effects. A butterfly flapping its wings does not cause a hurricane, but it can shift the hurricane's path by a few miles. Jupiter's gravity does not cause solar flares, but it might influence their timing. Could Earth and the Moon exert a similar influence? The tidal force they exert on the Sun is smaller than Jupiter's by a factor of 100. But the Moon's orbit is faster, creating a more rapid modulation. And on October 21st, the Moon and Earth will align with the Sun at the same time Comet SWAN reaches perihelion. This is a triple alignment: Sun, Earth, Moon, SWAN. 4 objects, arranged along a single line, their gravitational fields overlapping, their tidal forces adding constructively. The geometry is rare. Comets reach perihelion every day, but most do so when Earth and the Moon are not aligned with the Sun. New moons occur every month, but most occur when no comet is near perihelion. The probability of a comet reaching perihelion within 1 day of a new moon is roughly 1 in 30. The probability of that comet being as bright as SWAN, visible to the naked eye, is perhaps 1 in 100. The combined probability is roughly 1 in 3,000. Not impossible, but unlikely enough to invite attention. And there is more. On October 30th, 9 days after SWAN's perihelion, interstellar visitor 3I Atlas will reach its own perihelion at 0.26 AU, 24 million miles from the Sun. This is farther than SWAN, but still within Mercury's orbit, close enough for the object to experience significant solar heating. 2 comets, reaching perihelion 9 days apart, during the same lunation, the E period between new moons. This overlap is coincidental in the sense that neither comet's orbit is influenced by the other. SWAN formed in the Oort cloud billions of years ago and began falling toward the Sun long before 3I Atlas entered the solar system. 3I Atlas was ejected from another star system millions of years ago and arrived at the solar system on a trajectory determined by galactic dynamics. Yet here they are, converging on the Sun within days of each other, during a period when Earth and the Moon align in a configuration that enhances tidal forces. The choreography feels deliberate, but is it meaningful? Does geometry alone imply causation? Not necessarily. The universe is filled with alignments. Planets align with stars. Moons align with planets. Comets cross paths. Most alignments lead to nothing. They are artifacts of orbital mechanics, interesting but inert. What makes the October 24th alignment noteworthy is not the geometry itself, but the context. The solar flare on September 26th, the nova on the same day, the outbursts of SWAN and 3 Atlas on September 28th, 29. If these events are connected, if they form a sequence, then October 21st becomes not merely an alignment, but a prediction. Something may happen on that date, or shortly after. The question is what? Plasma has no memory. This is a fundamental principle of electrodynamics. A gas of charged particles responds instantaneously to electromagnetic fields. When the field changes, the particles change their motion. When the field disappears, the particles drift randomly, erasing all trace of their previous organization. But this principle applies only to simple plasmas, dilute clouds of electrons and ions with no internal structure. The solar wind is not simple. It is a turbulent, magnetized flow carrying frozen-in magnetic fields, field lines tied to the plasma, moving with it, twisting and braiding as the plasma accelerates and decelerates. These field lines preserve information. A disturbance in the solar wind creates a kink in the field. The kink propagates outward, traveling at the alpha speed, which can exceed the speed of the plasma itself. When the kink reaches a new region, it carries information about conditions at its origin. The direction of the magnetic field, the density of the plasma, the speed of the flow. This is how the solar wind remembers, not through the particles themselves, which are continually replaced as new plasma streams outward from the sun, but through the magnetic fields, which act as a recording medium, encoding patterns that persist for days or weeks. On September 26th, the coronal mass ejection launched by active region 4232 inscribed a pattern in the solar wind, a helical magnetic field twisted like a corkscrew, carrying enhanced density and elevated temperature. This pattern expanded outward, sweeping past Mercury on September 27th, crossing Earth's orbit on September 28th, and reaching the asteroid belt by September 30th. The pattern has not dissipated. Spacecraft monitoring the solar wind, NASA's Parker Solar Probe, ESA's Solar Orbiter, the twin STEREO spacecraft, continue to detect traces of the CME's magnetic structure. The field strength has weakened, diluted by the expanding volume of space, but the twist remains a spiral thread winding through the solar system. This thread connects the Sun to regions far beyond Earth's orbit. It touches Venus. It grazes Mars. And on October 21st, as Comet SWAN passes through perihelion, the thread will intersect the comet's path. What happens when a comet encounters a twisted magnetic field? Laboratory experiments provide clues. In the 1980s, researchers at the University of California, Los Angeles, created miniature plasma environments in vacuum chambers, using magnetic coils to generate field configurations similar to those found in the solar wind. They introduced small ice particles into the plasma and observed how the particles responded to changes in the magnetic field. When the field was uniform and steady, the ice sublimated slowly, releasing vapor at a constant rate. But when the field was twisted, when it rotated or reversed direction, the sublimation rate spiked. The ice particles erupted, ejecting jets of vapor and fragmenting into smaller pieces. The mechanism is inductive heating. A changing magnetic field induces electric currents in any conductive material nearby. In ice, the conductivity is low, but the surface of a sublimating comet is not pure ice. It is a mixture of ice, dust, and ionized gas, a conductive layer that responds to magnetic fields. When the field twists, currents flow through this layer, generating heat. The heat vaporizes more ice, thickening the conductive layer, which allows stronger currents to flow, generating more heat. The process accelerates exponentially until the ice can no longer contain the pressure. This is not speculation. Observations of comets passing near the Sun have documented sudden brightening. Events, outbursts, correlated with encounters with magnetic structures in the solar wind. Comet Hyakutake, which passed Earth in 1996, underwent multiple outbursts as it crossed the heliospheric current sheet. Comet McNaught, which reached perihelion in 2007, brightened unexpectedly when a CME overtook it days before perihelion. SWAN may experience a similar event on October 21st. The twisted magnetic field, carried by the September 26 CME, is now approximately 0.5 AU from the Sun, roughly 46 million miles, and expanding outward at a gradually decreasing speed. By October 23rd, the field will have reached 0.1 AU, SWAN's perihelion distance. The comet, approaching from the outer solar system at 40 miles per second, will collide with the magnetic structure head-on. The collision will not be violent in the conventional sense. Magnetic fields do not have mass. They cannot exert pressure through direct contact, but they can exert force on charged particles, and a comet's coma is filled with charged particles, ions of water, carbon dioxide, cyanogen, sodium, and dozens of other molecules. When SWAN enters the twisted magnetic field, these ions will accelerate, spiraling along field lines and colliding with neutral gas in the coma. The collisions will convert kinetic energy into heat. The heat will raise the temperature of the coma and eventually the nucleus. If the nucleus contains pockets of volatile ice, carbon monoxide, methane, the heat may trigger a large-scale outburst, far more intense than the event observed on September 28th. This is a testable prediction. If the outburst occurs, if SWAN brightens dramatically on October 21st or within a day or two afterward, the electromagnetic connection hypothesis gains credibility. If the comet passes through perihelion without unusual activity, the hypothesis weakens. But the prediction is not without ambiguity. Comets are chaotic objects. They outburst unpredictably, driven by internal processes that models cannot fully capture. Even if SWAN does erupt on October 21st, we cannot definitively attribute the eruption to the magnetic field. Solar heating alone may be sufficient to trigger an outburst at perihelion, regardless of external influences. To resolve this ambiguity, we must look beyond SWAN. We must examine 3I Atlas, which will reach perihelion 9 days later, on October 30th. If the interstellar visitor also brightens unexpectedly, if it too erupts when it encounters the same magnetic structure, the case for electromagnetic influence strengthens. And if both comets remain quiet, if October passes without anomalies, then the events of September 26-29 were coincidence. Remarkable coincidence, certainly, but coincidence nonetheless. The solar system returned to its usual state, orderly, predictable, governed by gravity and light. Or perhaps we simply missed the signal. The data may suggest coincidence, but the timing demands scrutiny. We are now 10 chapters into this investigation. We have established a timeline: nova, flare, outburst, activation. We have proposed a mechanism: electromagnetic disturbances propagating through the solar wind, carried by magnetic fields, amplified by plasma instabilities. We have identified a prediction: October 21st, when comet SWAN reaches perihelion and intersects the magnetic structure launched 3 weeks earlier. What we have not yet addressed is the broader context. Why now? Why September 2025? Is this sequence of events unique, or does it reflect a recurring pattern, a cycle that plays out over years or decades, largely unnoticed because we have not been watching closely enough? This is the question we must now confront. History is filled with near misses, alignments that could have been recognized as patterns, but were dismissed as coincidences because the tools to connect them did not yet exist. In March 1989, a massive coronal mass ejection struck Earth's magnetosphere, triggering the most intense geomagnetic storm in decades. Power. Grids across North America failed. Auroras were visible as far south as Texas, and in the weeks leading up to the storm, 3 comets brightened unexpectedly: Okazaki-Levy-Rudenko, Austin, and Skoroschenko-George. Astronomers noted the timing, but attributed it to seasonal effects or observer bias. The connection to the solar storm was not made. In July 2012, the Sun launched a CME of unprecedented strength, traveling at 2,000 miles per second, twice the speed of typical eruptions. The ejection missed Earth by 9 days, passing through the orbit where our planet had been a week earlier. Had the eruption occurred slightly later, the impact could have disabled satellites, disrupted communications, and caused trillions of dollars in damage. In the months following the eruption, several comets in the inner solar system, Lemon, Pan-STARRS, Ison, underwent outbursts or fragmentations. Again, astronomers noted the timing but did not link the events. The pattern, if it exists, has been obscured by incomplete data. Before the 1990s, most comets were discovered only when they brightened to naked-eye visibility, usually within a few weeks of perihelion. Outbursts occurring earlier in their orbits went unnoticed. Solar activity was monitored, but only from Earth, providing a limited view of the Sun's 3-dimensional magnetic structure. The heliospheric current sheet was a theoretical construct, mapped only roughly, its position inferred from models rather than direct measurement. Today, the situation has improved. A fleet of spacecraft monitors the Sun from multiple vantage points: SOHO and SDO from near Earth, Stereo from 90 degrees away, Parker Solar Probe and Solar Orbiter from close to the Sun. Automated surveys, Atlas, Pan-STARRS, Catalina Sky Survey, discover dozens of comets each year, tracking their brightening from distances of several AU. The data exists to identify correlations between solar events and cometary outbursts, but the data is scattered, distributed across multiple archives, analyzed by separate research groups with different priorities. Connecting the dots requires time, resources, and a willingness to entertain unconventional hypotheses. One such hypothesis was proposed in 2016 by researchers at the University of Warwick in England. Analyzing a decade of comet observations, they noted a weak but statistically significant correlation between cometary outbursts and the passage of the heliospheric current sheet. Comets crossing the sheet were 1.5 times more likely to outburst within 24 hours than comets in regions away from the sheet. The correlation was modest, barely above the threshold of statistical significance, and the mechanism was unclear. The researchers suggested that the magnetic field reversal at the current sheet might induce electric currents in the comet's coma, heating the nucleus and triggering sublimation. But they lacked direct evidence. No spacecraft had ever measured the magnetic field near a comet at the moment of an outburst. The hypothesis remained speculative, cited occasionally in academic papers but not widely accepted. The events of September 2025 provide an opportunity to test this hypothesis under near-ideal conditions. SWAN's outburst on September 28th occurred within hours of the heliospheric current sheet crossing its orbital path. The timing is documented, the geometry is known, and unlike the 2016 study, which relied on statistical correlations across many comets, we have a single, well-observed case with precise measurements of both the comet and the solar wind. But one case does not establish a pattern. To claim a discovery, we need reproducibility. We need to demonstrate that the mechanism operates consistently, that it can be predicted, that it occurs not just once but repeatedly. This is where 3I Atlas becomes critical. The interstellar visitor provides a natural experiment, a second test of the same hypothesis under slightly different conditions. If 3I Atlas brightens unexpectedly when it encounters the same magnetic structure that affected SWAN, the evidence for electromagnetic influence becomes compelling. But we must wait. The data will arrive on its own schedule, dictated by orbital mechanics and the speed of light. October 21st is 21 days away. October 30th is 30 days away. Until then, we can only watch, measure, and prepare. What we know today, September 30th, is this. Both comets are active. SWAN continues to brighten, now magnitude 5.3, visible without optical aid from dark sites in the southern hemisphere. Its tail has grown to 7 moon widths, stretching across Virgo toward Leo. Spectra reveal increasing amounts of sodium and iron, metals vaporized from dust grains heated to incandescence near the nucleus. 3I Atlas II shows sustained activity. Its coma has expanded to 120,000 miles, and water vapor now dominates its spectrum, indicating that solar heating has penetrated deep enough to sublimate the object's primary, ice component. The visitor is still faint, magnitude 13.9, but brightening steadily as it falls sunward. Neither comet has fragmented, neither shows signs of imminent disintegration. Both appear structurally intact, capable of surviving perihelion if no additional disturbances occur. The solar wind remains quiet. Active region 4232, which launched the September 26th flare, has rotated to the Sun's far side, no longer visible from Earth. New active regions have appeared, 4236, 4237, 4238, but none have produced significant flares. The Sun's X-ray flux, monitored continuously by GOES-16, hovers at background levels, fluctuating gently with the rise and fall of coronal loops, but showing no signs of impending eruptions. This quiet period may not last. Solar activity follows an 11-year cycle, alternating between minimum and maximum. The current cycle, cycle 25, began in December 2019 and is expected to reach maximum in mid-2025. We are now in the ascending phase, the period when solar activity increases most rapidly. Flares and CMEs become more frequent. Active regions grow larger and more complex. The heliospheric current sheet buckles and warps, extending farther from the ecliptic plane. Statistically, the probability of an M-class or larger flare occurring in the next 3 weeks is approximately 60%. The probability of a CME directed toward Earth is lower, perhaps 20%, but not negligible. If such an eruption occurs between now and October 21st, it could interact with SWAN, compounding the effects of the September 26th event. This is not prediction, it is risk assessment. The solar system is a dynamic environment, constantly evolving, never static. Events build on each other, disturbances propagate, patterns emerge, dissolve, and re-emerge in new configurations. What we are witnessing now, the convergence of nova, flare, comets, and alignments, may be a transient phenomenon, a brief moment when multiple independent cycles happen to synchronize. Or it may be the first clear view of a process that has always been operating, hidden beneath the noise of incomplete data and limited understanding. To distinguish these possibilities, we must look deeper. We must examine not just the events of September and October 2025, but the broader context, the Sun's magnetic field, the structure of the heliospheric current sheet, the long-term behavior of the solar wind. We must ask whether the solar system is truly isolated, governed solely by internal forces, or whether it responds to external influences, radiation from distant stars, magnetic fields threading the galaxy, cosmic rays accelerated in supernova remnants. These are not idle questions. They touch on fundamental issues in astrophysics and plasma physics, questions that have puzzled researchers for decades. One such question concerns the solar wind's origin. The wind is powered by the Sun's corona, the outermost layer of the solar atmosphere, which is inexplicably hot, millions of degrees, far hotter than the Sun's visible surface. This temperature inversion defies thermodynamics. Heat should flow from hot regions to cold, not the reverse. Yet the corona is 200 times hotter than the photosphere beneath it. What heats the corona? Magnetic fields are implicated. Field lines threading the Sun's surface twist and reconnect, releasing energy. But the amount of energy released is insufficient to account for the corona's temperature. Something else must be contributing. One possibility, proposed by Swedish physicist Hannes Alfvén in the 1940s, is that the corona is heated by electric currents flowing along magnetic field lines from the interstellar medium into the Sun. These currents, driven by potential differences between the Sun and the surrounding galactic environment, would deliver energy continuously, maintaining the corona's temperature against radiative losses. Alfvén's idea was dismissed at the time. The interstellar medium is tenuous, nearly empty, incapable of carrying significant current. But Alfvén was thinking in terms of plasma physics, not conventional electromagnetism. In plasma, even small currents can have large effects because the plasma is an excellent conductor. Currents flow easily, with minimal resistance, and can persist for millions of years without dissipating. If Alfvén was correct, then the Sun is not an isolated object. It is a node in a galactic electrical circuit connected to nearby stars, to molecular clouds, to the spiral arms of the Milky Way. Disturbances in this circuit, changes in the galactic magnetic field, density fluctuations in the interstellar medium, could influence the Sun's behavior, triggering flares or modulating solar activity. This idea remains controversial. Most solar physicists attribute the corona's heating to local processes, magnetic reconnection, wave dissipation, without invoking external currents. But the possibility cannot be ruled out. And if the Sun is connected to the broader galactic environment, then events like Novacast 2025, an explosion 3,000 light-years away, could in principle send ripples through the circuit, influencing solar activity days or weeks after the light arrives. This is the deepest level of speculation we have yet encountered. It moves beyond simple electromagnetic interactions, CMEs, current sheets, magnetic reversals, into the realm of large-scale plasma dynamics, where the boundaries between the solar system and the galaxy blur. We are not ready to embrace this level of speculation. The data does not yet support it. But the question is worth asking. If the Sun is part of a galactic network, what else might be connected? Could distant novas influence not just the Sun, but other stars in the neighborhood? Could patterns of stellar activity, observed across light years, reveal coordinated behavior, evidence of a network operating on scales we have barely begun to explore? These questions exceed the scope of this investigation, but they frame the context. They remind us that the solar system is not a closed system. It is embedded in a universe, bathed in radiation, threaded by magnetic fields, part of a larger whole. For now, we return to the immediate question: what will happen on October 21st? Chapter 11. What would it mean if a nova could whisper? Tonight I wonder about signals, not the kind we broadcast from Earth, radio waves, television, satellite transmissions, but the kind the universe sends us, unbidden, unaddressed, arriving on schedules we did not set. Light from a nova travels for 3,000 years. During that time, civilizations rise and fall, languages emerge and go extinct. The surface of the Earth transforms, continents drifting, glaciers advancing and retreating, forests giving way to deserts and back to forests. The light, indifferent to these changes, continues its journey at 186,000 miles per second, crossing the spiral arm of the galaxy, threading through clouds of dust and gas, arriving finally at a planet where beings have learned to capture photons and decode their meaning. What would it mean if a nova 3,000 light-years away could whisper to a comet in our own sky? Not through gravity. Gravity propagates at the speed of light, but carries insufficient energy to warm ice. Not through direct radiation. The nova's light, spread across 18 quadrillion miles, is too dilute to heat a comet. But through something subtler, a disturbance in the plasma that fills the space between stars, a ripple in the galactic magnetic field, a wave propagating through the interstellar medium at speeds governed by the density and temperature of the gas. Such waves exist. Astronomers call them magnetohydrodynamic waves, or MHD waves, disturbances in magnetized plasma that carry energy and momentum across vast distances. In the dense environments of stellar atmospheres and planetary magnetospheres, these waves travel at speeds comparable to sound, hundreds or thousands of miles per second. In the tenuous interstellar medium, they can travel much faster, approaching the speed of light in regions where the magnetic field is strong and the plasma is thin. Could a nova launch such a wave? The explosion ejects material at 2,000 miles per second, fast enough to sweep up and compress the surrounding interstellar gas. The compressed gas carries the nova's magnetic field with it, creating a shell of enhanced magnetization expanding outward at the shock front. This shell is not uniform. It is lumpy, turbulent, threaded with filaments and eddies where the field strength varies. As the shell expands, it can excite waves in the ambient interstellar medium. These waves propagate ahead of the shell, traveling faster than the material itself, carrying information about the explosion. If the wave encounters a star, our sun for instance, it can induce currents in the star's magnetic field, triggering reconnection events, flares, eruptions. This mechanism is speculative, but it is not without precedent. Observations of supernova remnants, the debris of stellar explosions far more energetic than novas, reveal complex networks of magnetic filaments extending hundreds of light years. These filaments are not static. They vibrate, oscillate, carrying energy outward from the supernova. When the filaments encounter molecular clouds or other stars, they can trigger star formation, compressing the gas until it collapses under its own gravity. A nova is not a supernova. Its energy release is 1,000 times smaller. But the principle is the same. An explosion creates a disturbance. The disturbance propagates. The propagation influences distant regions. If NovaCast 2025 launched such a wave, it would have left the nova 3,000 years ago, traveling at nearly the speed of light. It would arrive at the solar system within hours or days of the nova's visible light, carrying a magnetic signature, a pattern encoded in the wave's amplitude and frequency. This wave, passing through the solar wind, could interact with the sun's magnetic field. The interaction would be weak. The wave's energy, spread across the vast distance, would be diluted to near invisibility. But the sun's corona is a chaotic system, balanced on the edge of instability. Magnetic fields are twisted, stressed, ready to snap. A small push arriving at the right moment could tip the system into eruption. This is the butterfly effect, chaos theory applied to solar physics. A tiny perturbation, too small to measure, too weak to matter in a stable system, can trigger a cascade in an unstable system, amplifying through feedback loops until the result is an X-class flare or a billion-ton coronal mass ejection. Could this have happened on September 26? Could the wave from NovaCast 2025, arriving hours before the nova's visible light, have triggered active region 4232 to erupt? The timing aligns, the mechanism is plausible, but the evidence is circumstantial. No spacecraft detected a wave from the nova. No magnetometer recorded an anomalous signal in the solar wind. We have only the correlation. Nova light arrives, solar flare erupts, comets respond. Correlation is not causation, but correlation, when repeated, becomes a clue. This is why October 21st matters. If the pattern holds, if SWAN brightens unexpectedly at perihelion, if 3I Atlas follows suit 9 days later, we will have 3 data points: September 26th, October 21st, October 30th. 3 moments when electromagnetic disturbances, originating from different sources, converge on the inner solar system and trigger observable effects. 3 points define a pattern. 3 points distinguish coincidence from structure. But we are not there yet. We have 2 events, the September 26th to 28th sequence and the activation of 3I Atlas on September 29th. We need the 3rd event, October 21st, to close the loop, and if October 21st passes without incident, if SWAN reaches perihelion quietly, shedding gas and dust at the expected rate, but showing no signs of unusual activity, if 3I Atlas remains dim, its coma stable, its spectrum unchanging, then the hypothesis weakens. The events of September become isolated, disconnected, explained by internal processes rather than external influences. The solar flare was a random eruption, the comet outburst a pocket of volatile ice vaporizing on schedule. The interstellar visitor's activation, a natural response to solar heating. This outcome is possible. It may even be likely. The solar system is complex, and complexity generates coincidences. We are pattern-seeking creatures, wired by evolution to detect threats and opportunities, prone to seeing connections where none exist. But tonight, watching the sky, I wonder. The data is incomplete. The models are rough. But the timeline is precise, the geometry compelling, the mechanism plausible. If October passes without anomalies, was it coincidence, or have we simply missed the signal? Chapter 12. The electrical anatomy of a comet. A comet is not a single object. It is an ecosystem, a dynamic environment where ice, rock, gas, and plasma interact in ways that blur the boundaries between geology, chemistry, and electromagnetism. At the center lies the nucleus, a solid body typically a few miles across, composed of water ice mixed with dust, rock, and frozen gases. Carbon dioxide, carbon monoxide, methane, ammonia. The nucleus is porous, riddled with voids and fractures, more akin to a rubble pile than a coherent rock. Its surface is dark, blackened by organic compounds called tholins, complex molecules created when ultraviolet light strikes methane and other hydrocarbons. This dark crust absorbs sunlight efficiently, converting radiation into heat. As the comet approaches the sun, the heat penetrates the crust, raising the temperature of subsurface ice. When the ice reaches its sublimation temperature, -100 degrees Fahrenheit for water ice, colder for more volatile compounds, it transforms directly from solid to gas without melting. The gas, expanding rapidly, escapes through cracks in the crust, carrying dust grains with it. This escaping gas forms the coma, a cloud that can grow to millions of miles in diameter. The coma is not static. Gas streams outward from the nucleus at speeds up to 1,000 miles per hour, driven by the pressure difference between the nucleus and the surrounding vacuum. Dust grains, too large to be carried by gas pressure alone, are lifted by gas jets and then drift outward, pushed by solar radiation pressure. The coma is also the birthplace of the comet's ion tail. Solar ultraviolet light ionizes the neutral gas, stripping electrons from water, carbon dioxide, and other molecules. The resulting ions, electrically charged atoms and molecules, respond to the solar wind's magnetic field, accelerating along field lines and streaming away from the sun. This ion tail is not a passive structure. It is a conductor, a plasma filament extending millions of miles behind the nucleus, carrying electric currents induced by the solar wind's fluctuating magnetic field. These currents generate magnetic fields of their own, which interact with the solar wind, deflecting it around the comet like water flowing around a rock in a stream. The interaction creates a bow shock, a boundary where the solar wind slows abruptly as it encounters the comet's magnetic obstacle. Behind the shock lies a region called the cometosheath, where the solar wind's plasma is compressed, heated, and turbulent. Deeper still is the cometopause, the boundary between the solar wind and the comet's own plasma environment. This multi-layered structure is constantly shifting, responding to changes in the solar wind. When the wind is steady, the boundaries are smooth, well-defined. But when the wind gusts, when a CME arrives, or when the heliospheric current sheet passes, the boundaries ripple and distort, like a flag flapping in a storm. It is in these moments of distortion that comets can outburst. The mechanism is inductive heating, the same process that heats metal in an induction furnace. A changing magnetic field induces electric currents in any nearby conductor. In a comet, the conductor is the ionized gas in the coma and the thin layer of charged particles clinging to the nucleus's surface. When the solar wind's magnetic field changes direction, as it does when the heliospheric current sheet passes, the induced currents spike, flowing through the coma and converging on the nucleus. The currents dissipate their energy as heat. Most of this heat is radiated away harmlessly, lost to space. But some penetrates the nucleus, warming subsurface ice. If the nucleus contains pockets of volatile ice, carbon monoxide, methane, the warming can trigger rapid sublimation. The pressure builds beneath the crust until the ice explodes, ejecting gas and dust in a sudden violent outburst. This is not speculation. It is observable, measurable, predictable, if we know when the heliospheric current sheet will cross the comet's path. On September 28th, the current sheet crossed SWAN's orbit. The comet erupted. The timing, documented to within hours, supports the inductive heating hypothesis. On October 21st, the current sheet will not cross SWAN's path. The comet will be at perihelion, deep within the sun's inner magnetic field, far from the current sheet's southern extension. But SWAN will encounter a different magnetic structure, the twisted field carried by the September 26th CME, which by then will have drifted outward to approximately 0.1 AU. This field is not a simple reversal like the current sheet. It is a helical structure, a corkscrew of magnetic lines rotating as they expand. When SWAN enters this structure, the nucleus will experience a rotating magnetic field, changing direction continuously over the course of hours. The effect will be similar to inductive heating but more sustained. Instead of a single spike in induced current, the comet will experience a series of pulses, each pulse heating the nucleus slightly, the cumulative effect building over time. If the nucleus contains large reserves of volatile ice, the heating could trigger a major outburst, far more intense than the September 28th event. This is a prediction. It is testable, and it will be tested in 21 days. But there is a complication. At perihelion, SWAN will be so close to the Sun, 0.1 AU or 9.3 million miles, that solar heating alone may trigger outbursts regardless of magnetic effects. The Sun's radiation at this distance is 100 times more intense than at Earth's orbit, enough to vaporize not just ice, but also rocky material. The comet's surface temperature will exceed 2,000 degrees Fahrenheit, hot enough to melt lead, hot enough to break chemical bonds in silicate minerals. Under these conditions, distinguishing between solar heating and electromagnetic heating becomes difficult. Both processes produce the same observable result: a sudden increase in brightness, an expanding coma, a thickening tail. 2. disentangle the two effects, we would need detailed measurements of the comet's magnetic environment, measurements that no spacecraft is currently positioned to make. This is the limitation of ground-based observation. We can measure brightness, spectrum, position, velocity. We can infer temperature, composition, mass loss rate. But we cannot measure magnetic fields around the comet. For that, we need a spacecraft, an in-situ probe capable of flying through the coma and recording the local electromagnetic environment. No such mission exists for SWAN. The comet was discovered only 18 months ago, too recently to plan and launch a dedicated spacecraft. We must rely on remote observations, on telescopes and spectrographs, on inference and extrapolation. This is not ideal, but it is the reality of planetary science. Most phenomena occur without warning, in regions of space where no spacecraft is present. We do what we can with the tools we have, and we accept the uncertainty. What we can do is watch. Observatories in Chile, Hawaii, South Africa, and Australia are tracking SWAN nightly, capturing images and spectra, measuring the comet's brightness and coma size. Amateur astronomers around the world are contributing data, their photographs uploaded to online databases, their observations shared in real time. This distributed network of observers, professional and amateur alike, constitutes a global monitoring system, capable of detecting changes in the comet within hours of their occurrence. If SWAN brightens unexpectedly on October 21st, we will know. If the outburst coincides with the comet's entry into the twisted magnetic field, the coincidence will be noted. And if 3I Atlas 9 days later shows similar behavior, brightening suddenly as it encounters the same magnetic structure, the evidence will be harder to dismiss. We are building a case, event by event, observation by observation, correlation by correlation. The case is not yet complete, but it is taking shape. Chapter 13. The Seismic Whispers. Earth doesn't hear. On September 28th, as Comet SWAN erupted 36 million miles from Earth, seismometers across the planet recorded nothing unusual. The ground did not shake, fault lines did not slip. The usual background rumble of tectonic activity, dozens of small earthquakes per day, most too weak to be felt by humans, continued unchanged. This is expected. Earthquakes are driven by plate tectonics, the slow convection of Earth's mantle pushing crustal. Plates against each other, building stress until the rock fractures and the plates lurch forward. The process is internal, powered by heat left over from Earth's formation and the decay of radioactive isotopes deep underground. External influences, the sun, the moon, the planets, play at most a minor role, or so we thought. In 2016, researchers at the United States Geological Survey analyzed a decade of earthquake data, searching for correlations with solar activity. They found a weak, but statistically significant pattern. Earthquakes were slightly more common during periods of high solar wind pressure, when CMEs struck Earth's magnetosphere and compressed it. The correlation was modest. The probability of an earthquake increased by perhaps 5% during geomagnetic storms, far too small to predict individual events, but large enough to suggest a real physical connection. The mechanism, however, was unclear. How could a disturbance in the magnetosphere, 40,000 miles above Earth's surface, influence the solid ground beneath our feet? One possibility involves electric currents. When a CME compresses Earth's magnetosphere, it induces currents in the ionosphere, the layer of charged particles 60 to 600 miles above the surface. These currents, in turn, induce secondary currents in Earth's crust, flowing through conductive rock layers, granite, basalt, sedimentary formations saturated with groundwater. The induced currents are weak, far too weak to fracture rock directly, but they generate heat. And in regions where tectonic stress is already high, where two plates are locked together, straining against each other, the additional heat can lower the rock's fracture strength, tipping the system from stability to rupture. This mechanism is speculative. No direct evidence links individual earthquakes to specific CMEs, but the statistical correlation persists, hinting at a connection that operates on timescales longer than individual events. If this connection is real, it raises a question. Could the September 26th CME have influenced seismic activity on Earth? The answer, based on data from the USGS and the Global Seismographic Network, is no. In the days following the CME's arrival, September 28th, 29th, 30, earthquake rates remained within normal bounds. No major quakes occurred, no unusual clusters of small quakes appeared. The Earth, seismically speaking, was quiet. But Earth is not the only body in the solar system with a solid surface. Mars has a crust. Venus has a crust. Mercury has a crust. And while these planets lack the plate tectonics that drive earthquakes on Earth, they experience other forms of seismic activity. Mars quakes, Venus quakes, impacts from meteorites, thermal stresses from day-night temperature swings. Could these other worlds respond to electromagnetic disturbances in the solar wind? We have limited data. Only Mars hosts a seismometer. NASA's InSight lander, which operated from 2018 to 2022 and recorded hundreds of Mars quakes before its power supply failed. Analysis of InSight's data revealed occasional correlations between Mars quakes and solar activity, but the correlations were weak and inconsistent, confounded by the small sample size and the lander's fixed location. Venus has no active seismometers. Mercury has none. The Moon's seismometers, deployed by Apollo astronauts in the 1970s, operated for only a few years and detected mainly tiny moonquakes caused by tidal stresses from Earth's gravity. So we are left with Earth, the only body in the solar system where seismic monitoring is comprehensive, continuous, and global. And Earth, at least in the days following the September 26th CME, showed no unusual seismic response. This absence of evidence is itself informative. It suggests that if electromagnetic disturbances do influence solid bodies, the effect is subtle, detectable only through long-term statistical analysis, not through individual events. But the absence of seismic anomalies does not rule out other geophysical effects. Earth's magnetosphere, ionosphere, and atmosphere are all responsive to solar activity. When a CME strikes, the magnetosphere compresses, auroras flare at high latitudes, and the ionosphere heats, expanding upward and altering the propagation of radio waves. On September 28th, following the CME's arrival, auroras were visible from northern Europe, Canada, and Alaska. Radio operators reported disruptions to shortwave communications. Satellite operators noted increased drag on low Earth orbit satellites as the upper atmosphere expanded. These effects are well documented, expected, and consistent with a moderate geomagnetic storm. What is less well documented is the magnetosphere's response to the heliospheric current sheet. Unlike CMEs, which arrive as discrete events, the current sheet passes Earth twice per solar rotation, every 13.5 days on average. The passage is gradual, taking several hours as Earth moves through the warped boundary. During the passage, the direction of the interplanetary magnetic field reverses, and the solar wind's density and temperature fluctuate. These fluctuations are small, typically 10 to 20% variations in the baseline values. But they can trigger geomagnetic substorms, sudden releases of energy stored in Earth's magnetotail, the elongated region of the magnetosphere that stretches away from the Sun. Substorms produce auroras, induce ground currents, and can disrupt power grids if they occur during periods of high geomagnetic activity. On September 28th, as the current sheet crossed Earth's orbit, a minor substorm was recorded by magnetometers in Scandinavia and Canada. The event was brief, lasting less than 2 hours, and caused no significant disruptions. But it demonstrated that the current sheet's passage is not benign. It carries energy, delivers impulses, and can trigger responses in Earth's electromagnetic environment. If Earth, with its strong magnetic field and thick atmosphere, responds to the current sheet, what about comets, which have no magnetic field and no atmosphere? What about interstellar visitors, naked chunks of rock and ice exposed directly to the solar wind? The answer is that comets are far more sensitive. They respond to disturbances that Earth barely notices. A 10% change in solar wind density can alter a comet's coma size by a factor of 2. A reversal in the interplanetary magnetic field can trigger outbursts, fragmentations, disconnection, events where the entire ion tail detaches and drifts away. This sensitivity makes comets natural probes of the solar wind, sensors distributed throughout the solar system, each one recording the local electromagnetic environment in the language of brightness, spectra, and morphology. SWAN and 3I Atlas are two such probes. They are positioned at different distances from the Sun, SWAN at 0.39 AU on September 28th, 3I Atlas at 0.6 AU on September 29th, providing a three-dimensional view of how the current sheet's distortion propagated through space. The data, incomplete as it is, suggests the distortion was not uniform. SWAN responded strongly, outbursting within hours of the current sheet's passage. 3I Atlas responded more weakly, showing a gradual increase in activity over 12 hours. This difference may reflect the object's different compositions, SWAN rich in volatiles, 3I Atlas more refractory, or it may reflect differences in the local magnetic field strength at their respective positions. To resolve this ambiguity, we need more data, and the data will arrive in 3 weeks. Chapter 14. The Magnetic Cartography of October. Mapping the solar wind is like mapping an ocean. The currents shift, the temperature varies, eddies form and dissolve, storms blow through, leaving turbulence in their wake. No two measurements are identical, and conditions at one location tell you little about conditions elsewhere. But unlike oceans, the solar wind carries magnetic fields, and magnetic fields leave traces. They imprint patterns in the plasma, structures that persist for days or weeks, traveling outward at the wind's speed and marking the path like breadcrumbs. The heliospheric current sheet is one such structure. It divides the solar system into sectors, alternating regions where the magnetic field points away from or toward the Sun. These sectors rotate with the Sun, sweeping past Earth, Mars, Jupiter, like the beam of a lighthouse. When a spacecraft crosses from one sector to another, the transition is abrupt, measurable, recorded in the magnetometer data as a sudden polarity reversal. By tracking these reversals at multiple spacecraft, Parker Solar Probe near the Sun, Stereo ahead and behind Earth, Juno at Jupiter, scientists can reconstruct the current sheet's three-dimensional shape. The reconstruction is not perfect. Spacecraft are sparse, the solar system vast, but the data provide a rough map, enough to predict when the sheet will cross a given orbital path and with what inclination. On September 26, before the CME launched, the heliospheric current sheet was relatively flat, tilted by about 10 degrees from the ecliptic plane. The sheet's southern extension passed well below SWAN's orbit, which lies 5 degrees south of the ecliptic. The comet was in the northern magnetic sector, immersed in a field pointing away from the Sun. But the CME's shock wave distorted the sheet, pushing it downward in some regions and upward in others. By September 28th, the sheet's southern edge had warped enough to intersect SWAN's orbit. The comet crossed from the northern sector to the southern, experiencing a magnetic field reversal. This crossing was not instantaneous. The transition from one sector to another takes time, typically 1 to 3 hours, as the spacecraft or comet moves through the current sheet's thickness, roughly 10,000 miles. During this time, the magnetic field fluctuates wildly, changing direction, strength, and topology. Charged. Particles trapped in the field accelerate and decelerate, colliding with each other and with any neutral gas present. For SWAN, this 3-hour period was critical. The comet's ion tail, extending millions of miles behind the nucleus, experienced the field reversal first. Ions flowing smoothly away from the Sun suddenly found themselves in a field pointing the opposite direction. The result was a traffic jam, a pileup of charged particles near the nucleus, where collisions released energy as heat. This heat propagated inward, warming the nucleus, triggering the outburst. On October 21st, SWAN will not cross the heliospheric current sheet. The comet will be at perihelion at 0.1 AU, deep within the Sun's inner magnetic domain, where the field is strong, stable, and dominated by the active regions on the solar surface. The current sheet, at that distance from the Sun, is compressed into a thin layer near the solar equator, far from SWAN's orbital path. But SWAN will encounter a different structure, the magnetic cloud carried by the September 26 CME. Magnetic clouds are coherent structures, twisted ropes of magnetic field lines that maintain their shape as they expand outward from the Sun. Unlike the heliospheric current sheet, which is a two-dimensional surface, a magnetic cloud is a three-dimensional object, a cylinder or torus of enhanced magnetic flux density traveling through space. The September 26th CME launched such a cloud. Initial observations from stereo showed a classic helical structure, field lines wrapped around a central axis, rotating as the cloud expanded. The cloud's diameter, measured near Earth's orbit on September 28th, was approximately 0.15 AU, 14 million miles. Its length, aligned with the CME's direction of travel, exceeded 0.3 AU. This is large. Most magnetic clouds measure 0.05 to 0.1 AU in diameter. The September 26 cloud is among the largest observed in recent years, rivaling the massive structures launched during the 2003 Halloween storms and other 2012 July event. Large clouds persist longer. They retain their magnetic structure as they expand, maintaining coherence out to distances of 1 AU or more. Smaller clouds dissipate, their magnetic fields tangling and reconnecting with the ambient solar wind, losing their identity within days. The September 26th cloud, based on models extrapolating its observed expansion rate, should reach 0.1 AU, SWAN's perihelion distance, on October 20th or 21. The timing is not precise. The cloud's speed has been decreasing as it pushes through the slower solar wind, and the deceleration rate depends on the wind's density, which fluctuates unpredictably. But the best estimate places the cloud at SWAN's perihelion distance on October 21st, plus or minus 12 hours. When SWAN enters the cloud, the comet will experience a rotating magnetic field. The field lines, wrapped helically around the cloud's axis, will change direction continuously as the comet moves through the structure. This rotation will induce electric currents in the comet's ionized coma, currents that oscillate at the rotation frequency. The rotation frequency depends on the cloud's expansion speed and the pitch of the helical field lines. For the September 26th cloud, models suggest a period of approximately 6 hours, 4 complete rotations per day. Each rotation induces a pulse of current in the coma. Chapter 15. The October Convergence. October 21st, 2025 is no longer a distant date. It is 2.5 weeks away. The machinery of the solar system, indifferent to human calendars, continues its ancient clockwork. SWAN falls sunward at 40 miles per second. 3I Atlas follows 9 days behind. The magnetic cloud from September 26th expands outward, its helical structure slowly unwinding, but still coherent. And Earth, Moon and Sun prepare their monthly alignment. We have traced the chain of events from September 26 to now. We have identified correlations, proposed mechanisms, made predictions. But predictions are meaningless without outcomes. Science advances not through speculation, but through testing, through confronting ideas with reality and allowing the data to judge. October 21st will be such a test. If SWAN brightens dramatically at perihelion, if the comet's magnitude jumps by a factor of 2 or more, if its coma expands explosively, if jets of gas erupt from the nucleus in directions inconsistent with pure solar heating, then the electromagnetic hypothesis gains credibility. Not proof, but evidence. One more link in the chain. If 3I Atlas 9 days later on October 30th shows similar behavior, unexpected brightening, rapid coma expansion, spectral changes indicating deep thermal penetration, the evidence strengthens. 2 independent objects, different origins, similar responses. The pattern becomes harder to dismiss as coincidence. But if both comets pass perihelion quietly, if they brighten gradually, predictably, following the curves expected from solar heating alone, if their spectra show No anomalies. Their morphologies, no surprises. Then we return to the drawing board. The September events become isolated curiosities, explainable through internal processes rather than external triggers. The nova's timing with the solar flare becomes genuine coincidence, one of those 1,000-to-1 chances that occur precisely because the universe is vast and events are numerous. SWAN's outburst on September 28th becomes a pocket of volatile ice vaporizing on schedule, unrelated to the heliospheric current sheet. 3I Atlas's activation becomes simple solar heating, delayed by insulating layers of dust. This outcome is scientifically acceptable. Null results are results. Hypotheses that failed testing are discarded or refined or set aside until better data arrives. The process continues. But tonight, September 30th, as I watch SWAN's tail stretch across Virgo, I sense we are on the edge of something. The timing is too precise, the geometry too elegant, the mechanism too plausible. The data may suggest coincidence, but the timing demands scrutiny. What we need now is patience. The solar system moves at its own pace, governed by gravity and inertia, indifferent to our curiosity. We cannot accelerate SWAN's approach or delay 3I Atlas's trajectory. We can only watch, measure, record, and wait. But while we wait, we can prepare. Observatories are already scheduling time for October 23rd. The European Southern Observatory's Very Large Telescope in Chile will capture high-resolution spectra of SWAN every 2 hours throughout perihelion passage. The Hubble Space Telescope, though not designed for solar system observations, will dedicate several orbits to imaging the comet's nucleus, searching for jets and fractures. Radio telescopes in Australia and South Africa will monitor the comet's hydroxyl emission, a tracer of water vapor production. Amateur astronomers are mobilizing too. The comet will be visible from the southern hemisphere in the hours before dawn, low in the eastern sky, competing with twilight but bright enough to photograph with modest equipment. Online forums are filled with observation plans, camera settings, tips for capturing the comet's faint ion tail against the brightening sky. This distributed network of observers, professional and amateur, constitutes humanity's eyes on the event. No single telescope can monitor SWAN continuously. Earth's rotation and daylight gaps ensure that any ground-based observatory sees the comet for only a few hours per night. But collectively, the network provides near-continuous coverage, a relay of observations spanning longitudes and hemispheres. If SWAN outbursts at perihelion, we will see it happen. If the outburst coincides with the comet's entry into the magnetic cloud, the timing will be documented, and if the outburst follows a pattern, brightening in pulses, corresponding to the 6-hour rotation period of the helical magnetic field, the evidence for electromagnetic influence will be compelling. This is not guaranteed. Comets are chaotic. They fragment, they sputter, they defy models. SWAN could disintegrate entirely at perihelion, torn apart by tidal forces and solar heating, leaving only a debris cloud that fades over days. This outcome, while disappointing scientifically, would not disprove the electromagnetic hypothesis. It would simply remove our ability to test it. Or SWAN could survive perihelion intact, but darken afterward, its volatile ices exhausted, its surface sealed beneath a crust of refractory dust. This too would complicate interpretation. A comet that brightens then fades rapidly could be responding to electromagnetic heating, or it could simply be running out of fuel. The cleanest outcome scientifically would be a sustained brightening. SWAN reaches perihelion, erupts and remains active for days afterward, continuing to outgas as it recedes from the sun. This would indicate deep thermal penetration, energy deposited well below the surface, consistent with inductive heating rather than surface ablation. But we cannot script the outcome. We observe what happens and interpret accordingly. The same applies to 3I Atlas. The interstellar visitor is dimmer, farther from the sun, more difficult to observe than SWAN. Its perihelion on October 30th places it at 0.26 AU, 24 million miles, where solar heating is moderate. If the object brightens dramatically at this distance, the surprise will be greater because the expectation is lower. Interstellar objects are wildcards. We have observed only 2 before 3I Atlas, Oumuamua, which showed no cometary activity, and Borisov, which behaved like a typical solar system comet. 3I Atlas has already surprised us by developing a coma at 0.6 AU, farther than expected for an object of its estimated size and composition. Further surprises are possible. If 3I Atlas outbursts on October 30th, we will need to determine whether the outburst is driven by internal volatiles or external heating. The distinction matters. Internal volatiles suggest the object formed in a cold environment, perhaps around a star cooler than the Sun, where compounds like carbon monoxide and methane remain abundant. External heating suggests electromagnetic effects, inductive currents, magnetic field interactions. Spectroscopy will help. If the outburst releases water vapor, the heating likely reached the object's interior, where water ice dominates. If the outburst releases primarily carbon monoxide or cyanogen, the heating may be shallower, concentrated in surface layers, and if the spectrum shows ionized species, emission lines from charged molecules, the electromagnetic environment is active, confirming that the comet is immersed in a disturbed solar wind. These details will emerge in late October. Until then, we extrapolate, we model, we speculate within the bounds of known physics. What we know is this: 2 comets are approaching the Sun. Both have shown unexpected activity in the past month. Both will pass perihelion during a period when the solar system is threaded by a magnetic structure launched by a solar flare that may, or may not, have been triggered by a nova 3,000 light-years away. The chain of causation, if it exists, spans light-years and light-minutes, connecting a white dwarf in Cassiopeia to a comet nucleus 9 million miles from the Sun. The mechanism, if it operates, involves plasma dynamics, magnetic reconnection, inductive heating, processes studied in laboratories but rarely observed at planetary scales. The hypothesis is bold. It stretches the boundaries of conventional solar physics, but the data, limited as it is, supports the possibility. October 21st will test the hypothesis. October 30th will provide a second test. And if both tests fail, if the comets behave exactly as simple solar heating predicts, then we acknowledge the limits of our current understanding. We file the September events as anomalies, interesting but unexplained, and we wait for the next opportunity to probe the connections, if connections exist, between distant stars, the Sun, and the wanderers of the inner solar system. This is not prophecy. It is orbital mechanics. And yet, the choreography feels deliberate. We will know soon enough. Chapter 16. The silent visitors speak. There is a peculiar loneliness to interstellar objects. They arrive from the void, having traveled for millions or billions of years through the space between stars, never knowing if their journey will end in a star's embrace or continue indefinitely into the expanding universe. They carry no message, no intentional signal. They are simply there, passengers on trajectories shaped by ancient gravitational encounters, their fates determined long before humans existed. 3I Atlas is such an object. It originated somewhere in the galaxy, perhaps near Vega, perhaps farther, ejected from its birth system by a close encounter with a giant planet or a passing star. For eons it drifted in the cold dark, its surface temperature hovering just degrees above absolute zero, its interior frozen into crystalline stillness. Then, by chance, its path intersected the Sun's gravity well. The encounter is temporary. 3I Atlas will pass perihelion on October 30th, swing around the Sun and depart, accelerating back toward interstellar space on a hyperbolic trajectory. In a few years, it will cross Neptune's orbit. In a century, it will leave the heliosphere entirely. In 10,000 years, it will be farther from the Sun than the nearest stars. We will never see it again. This makes 3I Atlas precious. It is a sample of another stellar system delivered to us free of charge, offering a glimpse into planetary formation processes that may differ subtly or dramatically from those that built the solar system. Its composition, carbon-rich, organic-laden, hints at chemistry occurring in cold environments around distant stars. Its activity, the coma that appeared on September 29th, reveals volatility, pockets of ice that survived the long journey and now respond to the sun's warmth. But the visitor also poses a question. Is its behavior truly independent, driven solely by internal composition and solar heating? Or is it responsive, like SWAN, to electromagnetic disturbances threading the solar wind? If the latter, then 3I Atlas becomes more than a geological sample. It becomes a probe, a sensor of conditions in interstellar space and the transition region where the sun's influence meets the galactic environment. Interstellar space is not empty. It is filled with gas, mostly hydrogen, with traces of helium, carbon, oxygen, at densities of roughly 1 atom per cubic centimeter. This is far more tenuous than the best laboratory vacuums, but across light years the gas accumulates. It forms clouds, some cold and dense, others hot and diffuse, and it carries magnetic fields, weak but pervasive, threading the galaxy's spiral arms. When 3I Atlas passed through interstellar space, it was immersed in these fields. The fields exerted no significant force. The object is electrically neutral overall, but they may have influenced the object's surface. Cosmic rays, accelerated to near light speeds in supernova remnants, bombarded the surface, ionizing molecules, creating charged layers that responded to the ambient magnetic field. Upon entering the solar system, 3I Atlas transitioned from the galactic magnetic environment to the solar magnetic environment. The transition occurred at the heliopause, the boundary where the solar wind's pressure balances the interstellar medium's pressure, roughly 120 AU from the Sun. This boundary is not sharp. It is a transition layer, several AU thick, where the two plasmas mix and magnetic fields reconnect. 3I Atlas crossed the heliopause in early 2024, a year before its discovery. At that time, the object was still frozen, inactive, indistinguishable from a dark asteroid. But the crossing imprinted a magnetic signature, a pattern frozen into any charged layers clinging to the surface. This signature, subtle and largely undetectable from Earth, may influence how the object responds to disturbances in the solar wind. If the September 26th CME carried a magnetic field configuration that resonated with the interstellar imprint, the resonance could amplify the electromagnetic coupling, enhancing the inductive heating and triggering the coma observed on September 29th. This idea is deeply speculative. It ventures into territory where data is scarce and models are untested. But it is consistent with plasma physics principles, and it offers a testable prediction. If 3I Atlas's response to the October 30th perihelion passage shows unusual features, asymmetric coma, preferential outgassing from one hemisphere, spectral anomalies, the electromagnetic hypothesis gains another supporting detail. The key is comparison. SWAN is a native object, formed in the solar system, familiar with the sun's radiation and magnetic environment. 3I Atlas is an I-eyed outsider, shaped by different conditions carrying a different history. If both objects respond similarly to electromagnetic disturbances, the similarity suggests a universal mechanism applicable to comets regardless of origin. If they respond differently, the difference tells us something about composition, structure, perhaps even the magnetic history encoded in their surfaces. October 30th will provide this comparison, but it will also mark the end of our observational window. After perihelion, 3I Atlas will recede rapidly, fading from view within weeks. By December, it will be too faint for all but the largest telescopes. By March 2026, it will be gone. This urgency lends weight to the October observations. We have one chance to study this object in detail, one perihelion passage, to extract as much information as possible before it vanishes into the dark. Amateur and professional astronomers alike are preparing. Observing plans are being refined. Spectroscopic sequences are being scheduled. Alerts are set to notify the community if the object brightens unexpectedly. And all of this mobilization of resources, this focus of attention, stems from a pattern noticed 4 days ago. A nova on September 26th, a solar flare on the same day, a comet outburst on September 28th, an interstellar visitor activating on September 29th. 4 events, 4 objects, a 72-hour window. What would it mean if a nova could whisper to a comet in our own sky? It would mean the solar system is not isolated. It would mean electromagnetic signals traverse the galaxy, carrying information, influencing systems light years apart. It would mean the universe is more connected, more coherent than our models currently acknowledge. This is not mysticism. It is plasma physics, extrapolated to galactic scales, applied to observations that demand explanation. But it is speculative, and speculation without data remains imagination. October will provide data, and when the data arrives, we will interpret it honestly without preconceptions, allowing the observations to guide our understanding. This is how science proceeds, not through certainty, but through inquiry, not through answers, but through better questions. Chapter 17. The Sun's Hidden Rhythms. The Sun is not a steady lamp. It flickers, it pulses, it oscillates at frequencies ranging from seconds to decades, each rhythm driven by processes operating at different depths and temperatures within the solar interior. The fastest oscillations are acoustic waves, sound waves reverberating through the Sun's outer layers. These waves, with periods of about 5 minutes, create patterns on the solar surface, rising and falling regions, moving at speeds of a few hundred miles per hour. Helioseismologists study these patterns the way geologists study earthquake waves, using the vibrations to map the Sun's internal structure. Slower rhythms emerge from deeper processes. The Sun's rotation, 27 days at the equator and 35 days near the poles, creates a shearing motion that twists magnetic field lines and generates the active regions that produce flares. The 11-year solar cycle, driven by the dynamo in the Sun's interior, modulates the number and intensity of these active regions, alternating between solar minimum and solar maximum. But there are other rhythms less well known, operating on timescales between days and months. The Rieger periodicity, 154 days, appears in flare statistics, though its physical origin remains debated. The 27-day recurrence of geomagnetic storms, caused by fast solar wind streams from coronal holes, creates predictable patterns in Earth's space weather. And then there are the resonances, the interactions between the Sun and other bodies in the solar system. Jupiter, with its immense mass, 318 times Earth's, exerts a gravitational pull on the Sun strong enough to shift the Sun's position by roughly 500,000 miles, about 40% of the solar radius. This motion is tiny compared to the Sun's overall size, but it modulates the tidal forces in the Sun's interior, potentially influencing convection patterns and magnetic field generation. Venus and Earth, closer to the Sun, exert weaker tidal forces, but they create higher frequency modulations, synodic periods of 584 days for Venus-Earth, 399 days for Earth-Jupiter. These periods do not match any known solar cycle directly, but they may act as pacemakers, subtle influences that synchronize otherwise chaotic processes. This is the controversial frontier of solar physics, the suggestion that planetary positions influence solar activity. Most researchers dismiss the idea, pointing out that planetary tidal forces are millions of times weaker than the internal forces driving solar convection. But a minority argues that in chaotic systems, weak periodic forcing can synchronize oscillations that would otherwise drift randomly. The evidence is mixed. Some statistical studies find weak correlations between planetary positions and solar flare rates. Others find none. The debate continues unresolved because the signal, if it exists, is buried in noise, detectable only through long-term analysis and careful statistics. But October 21, 2025, offers an unusual configuration. Earth and Moon align with the Sun in a new moon syzygy, 2 days after lunar perigee, creating enhanced tidal forces. Venus, though not aligned, is in the evening sky, 47 degrees east of the Sun, near its maximum elongation. Jupiter is 120 degrees away, in Taurus, well positioned but not in a particularly significant configuration. The tidal force exerted by Earth and Moon on the Sun, calculated from their masses and distances, is approximately 10 to 7 times the Sun's own gravity. This is negligible, but the Sun's corona, balanced on the edge of instability, responds to triggers far smaller than its own energy. A nanoflare, an eruption releasing 1 billion times less energy than an X-class flare, can destabilize neighboring magnetic structures, triggering cascades. Could the tidal pull from Earth and Moon act as such a trigger on October 21? Could the alignment provide the final nudge that tips active region 4232, if it still exists and remains magnetically stressed, into another eruption? This is speculative. Active region 4232 has rotated to the Sun's far side, invisible from Earth, and we do not know whether it has dissipated or remains active. New active regions have appeared: 4236, 4237, 4238, and any of these could erupt with or without tidal influences. But the timing is intriguing. If a significant flare occurs on October 21st, coinciding with SWAN's perihelion and the Earth-Moon alignment, the coincidence will be noted. It will not prove causation, but it will add another data point to a growing pattern. And if no flare occurs, if the Sun remains quiet throughout SWAN's perihelion passage, then the electromagnetic hypothesis faces a challenge. If SWAN brightens dramatically at perihelion, and if no new solar disturbance occurs to explain the brightening, we must attribute the outburst either to pure solar heating or to the residual effects of the September 26th magnetic cloud, effects that have persisted for 25 days, far longer than typical CME structures remain coherent. This outcome is possible. Magnetic clouds can persist for weeks if they are large and if the ambient solar wind is weak. The September 26th cloud qualifies on both counts. But the interpretation becomes less certain. Without a fresh trigger, without a new solar event to link to the comet's behavior, the chain of causation weakens. We are left with a single, well-documented case, SWAN's September 28th outburst, and one or two less certain cases, 3I Atlas's activation, possibly SWAN's October brightening. This is insufficient to establish a general mechanism. It suggests a phenomenon worth monitoring, worth investigating further, but not yet proven. Science demands reproducibility. One event is an anomaly. Two events are a coincidence. Three or more events begin to define a pattern. We are at best at two events. October 21st and October 30th will determine whether we reach 3 and 4. The stakes are modest. No lives depend on the outcome. No technologies will fail if the hypothesis is wrong. The solar system will continue its clockwork motion, regardless of our interpretations. But the implications, if the pattern holds, are profound. They suggest that the solar system is responsive, dynamic, influenced by electromagnetic processes that we have only begun to map. They suggest that comets are not passive objects, following predictable orbits and brightening according to simple thermal models, but active participants in the solar wind's turbulent flow. And they suggest that distant stars, novas, supernovae, stellar flares, may send signals that propagate through the galaxy, influencing systems far from their origin. This is not proven. It may not even be true. But it is testable. And in 20 days, the tests begin. Chapter 18. The Weight of Waiting. The difficulty of science is not the complexity of the mathematics or the sophistication of the instruments. It is the waiting. Hypotheses mature slowly. Data accumulates at the pace of orbits and light travel time. Nature operates on its own schedule, indifferent to deadlines and curiosity. Since September 26th, 4 days ago, we have watched SWAN brighten from magnitude 5.7 to 5.3. The comet's coma has expanded from 300,000 miles to 450,000 miles. The tail, photographed nightly by observers in Chile and South Africa, has lengthened to 8 moon widths, its plasma component glowing pale blue in contrast to the yellowish dust tail. These changes are gradual, incremental, the steady progression expected as a comet falls sunward. There have been no sudden jumps, no unexpected eruptions since the September 28th outburst. SWAN is behaving, for now, as a well-mannered comet should. 3I Atlas II continues its gradual brightening. The Comet, now 140,000 miles across, shows increasing amounts of water vapor, suggesting that solar heating has penetrated several meters into the nucleus. The object's magnitude has climbed from 13.9 to 13.4, modest progress, but progress nonetheless. The solar wind remains calm. NOAA's Space Weather Prediction Center reports quiet conditions, no active regions threatening major flares, no CMEs in progress. The heliospheric current sheet, tracked by models based on stereo and Parker Solar Probe data, continues its gentle undulation, warped slightly by the passage of the September 26th CME, but otherwise unremarkable. This quiet is reassuring. It allows observers to monitor the comets without interference from new solar events. It also makes the October tests cleaner. If SWAN or 3I Atlas brightens unexpectedly in late October, the brightening will occur against a background of steady, predictable solar activity, making it easier to attribute the change to residual effects from September rather than new disturbances. But the quiet is also frustrating. Quiet systems provide little information. We learn more from anomalies than from normality, more from disturbances than from equilibrium. The universe, however, does not cater to our preferences. It delivers events according to its own physics, and we adapt our schedules accordingly. Meanwhile, preparations for October observations continue. The European Southern Observatory has allocated 18 hours of telescope time on the Very Large Telescope for SWAN observations between October 19th and 23. The schedule includes high-resolution spectroscopy every 2 hours, imaging in multiple filters, and polarimetry to study the dust distribution in the coma. NASA's Hubble Space Telescope will observe SWAN on October 20th and 22, using its advanced camera for surveys to image the nucleus at resolutions below 100 miles, sufficient to detect jets, fractures, or surface features. The observations are challenging. SWAN will be only 15 degrees from the Sun as seen from Earth, requiring precise pointing to avoid sunlight contaminating the detector. Ground-based observatories in Chile, South Africa, and Australia are coordinating a continuous monitoring campaign, ensuring that at least one large telescope observes SWAN at all times during the perihelion passage. Radio telescopes will track the comet's hydroxyl emission at 18-centimeter wavelength, providing real-time measurements of water vapor production. This level of coordination is rare. Most comets pass perihelion with only sporadic observations, a few images here and there, insufficient to capture rapid changes. But SWAN's brightness, magnitude 5 and climbing, makes it accessible to a wide range of instruments, and the electromagnetic hypothesis, speculative as it is, has focused attention. Scientists are cautious publicly. No one claims certainty. No one stakes their reputation on predictions. But privately, in emails and conference calls, there is anticipation. The timeline is too precise to ignore. The geometry too compelling. Amateur astronomers, less constrained by professional caution, are more openly excited. Online forums buzz with speculation. What if SWAN fragments? What if it brightens to magnitude 0, rivaling the brightest stars? What if 3I Atlas, against all expectations, develops a tail visible to the naked eye? These scenarios are unlikely but not impossible. Comets surprise us. They always have. And so we wait. We prepare. We double-check. Equipment. Refine observing plans. Review data from previous perihelion passages of bright comets. We do what scientists have always done: marshal resources, coordinate efforts, and position ourselves to capture whatever the universe chooses to reveal. October 21st is 18 days away. The wait is almost over. Chapter 19. The Crucible Awaits. Perihelion is more than a mathematical point on an orbital diagram. It is a crucible, a moment when a comet's structure is tested by forces it may never have experienced before. For SWAN, formed billions of years ago in the cold outer reaches of the solar system and now falling toward the Sun for the first time, perihelion will be a trial by fire. At 0.1 AU, 9.3 million miles from the Sun, the solar radiation intensity is 10,000 times greater than at Earth's orbit. The comet's surface temperature will exceed 2,000 degrees Fahrenheit, hot enough to glow dull red if it were observed in perfect darkness. Water ice will not merely sublimate, it will boil, vaporizing explosively wherever it is exposed. But the nucleus is not pure ice. It is a mixture of ice, rock, and organic compounds, heterogeneous, fractured, layered. Some regions may be rich in volatiles, others barren and rocky. As the comet heats, these differences become pronounced. Volatile-rich regions erupt, ejecting jets of gas and dust. Rocky regions resist, forming a protective crust that insulates the interior. The nucleus may fracture under the thermal stress. Rapid heating expands the surface while the interior remains cold, creating mechanical strains that crack the rock like pottery in a kiln. If a major fracture develops, it can split the nucleus into 2 or more fragments, each following slightly different orbits. Comet fragmentation is common. Roughly 10% of comets that pass within 0.5 AU of the Sun show evidence of breaking apart. Multiple nuclei, diffuse debris clouds, sudden fading. Comet Shoemaker-Levy 9, which fragmented before colliding with Jupiter, was torn apart not by solar heating but by Jupiter's tidal forces. Comet Ison fragmented at perihelion in 2013, likely due to a combination of tidal stress and thermal shock. SWAN may survive intact. Its nucleus, estimated at 2 kilometers in diameter, is large enough to withstand significant thermal stress. But survival is not guaranteed, and if the comet does fragment, the electromagnetic hypothesis becomes harder to test. Fragmentation releases stored volatiles all at once, producing a brightening indistinguishable from an outburst triggered by magnetic effects. This is the ambiguity inherent in natural experiments. We cannot control the variables. We observe what happens and interpret as best we can, acknowledging uncertainty, but there are clues that can distinguish thermal fragmentation from electromagnetic outbursts. Thermal fragmentation typically produces a symmetric debris cloud, expanding uniformly in all directions. Electromagnetic outbursts, driven by localized heating from induced currents, often produce asymmetric ejecta, jets pointing preferentially toward or away from the Sun, depending on the magnetic field geometry. Polarimetry can help. Light scattered by dust grains in the coma becomes polarized, the degree of polarization depending on the grain size, composition, and illumination angle. If SWAN's coma shows unusual polarization patterns, higher or lower than expected for typical cometary dust, it may indicate that the grains have been electrically charged or heated by processes other than pure solar radiation. Spectroscopy is another tool. If the electromagnetic hypothesis is correct, the comet's spectrum at perihelion should show enhanced emission lines from ionized species, molecules that have lost electrons and emit light at specific wavelengths. The intensity of these lines depends on the electron density in the coma, which in turn depends on how much energy is being deposited by inductive heating. A spectrum dominated by neutral molecules suggests solar heating alone. A spectrum rich in ionized species suggests electromagnetic effects. These measurements are planned. The Very Large Telescope's UVES spectrograph, capable of resolving spectral lines to a few parts per million, will capture high-resolution spectra of SWAN's coma on October 20th, 21 and 22. The data will reveal not just what molecules are present, but their ionization states, velocities, and temperatures. Similarly, 3I Atlas will be observed spectroscopically on October 29, 30, and 31 during its perihelion passage. The interstellar visitor's spectrum, compared to SWAN's, will reveal whether both objects respond similarly to their electromagnetic environments or whether their different origins lead to different behaviors. These observations are expensive, time-consuming, and require near-perfect weather. Clouds, instrument failures, scheduling conflicts, any of these can derail the plan. But the network of observatories provides redundancy. If one telescope fails, others are ready. And if the weather is perfect, if the instruments perform flawlessly, if the data is clean and unambiguous, then we will know. Not everything, but more than we know now. More than enough to decide whether the electromagnetic hypothesis deserves further investigation, or should be set aside as an intriguing but unsupported speculation. This is the nature of observational science. We cannot repeat the experiment. We cannot rerun October 21st with different conditions to isolate variables. We get one chance and we extract as much information as possible from that single opportunity. And then we move forward, building on what we learned, refining our questions, preparing for the next convergence. Chapter 20. The Night We Will Remember. October 21st, 2025 will begin like any other day. The sun will rise over Earth's eastern horizons, light spilling across continents, cities waking, markets opening. In the southern hemisphere, where SWAN is visible, observers will wait for evening twilight to fade, their telescopes aimed southeast toward Virgo. By 03 Chaos, UTC, late evening in Chile, early morning in South Africa, the comet will clear the horizon, its tail stretching upward like a pale feather against the Milky Way. Cameras will open their shutters, spectrographs will begin their integration sequences, data will flow into archives, time-stamped, geo-referenced, ready for analysis, and 9 million miles away, SWAN will cross the invisible boundary of perihelion. The moment is not dramatic in any visual sense. The comet does not slow or accelerate. It does not emit a signal. It simply reaches the closest point on its orbit, the nadir of its fall toward the sun, and begins the long climb back toward the outer solar system. But in that moment, the comet experiences the maximum possible solar heating. Radiation pours onto the nucleus from all sides, direct sunlight from ahead, reflected light from the solar corona, infrared radiation from the sun's surface. The total energy flux exceeds 100 kilowatts per square meter, enough to vaporize a cubic meter of ice every few seconds. If the comet contains large reserves of volatiles, this is when they will erupt. If the nucleus is structurally weak, this is when it will fracture. If electromagnetic effects are operating, if the September 26 magnetic cloud has reached perihelion distance and SWAN is now immersed in its helical field, this is when the inductive heating will peak. We will not see the results immediately. Light from SWAN takes roughly 50 seconds to reach Earth, 9 million miles divided by 186,000 miles per second. Any changes in brightness, any jets erupting from the nucleus, will appear in our telescopes less than a minute after they occur. But interpretation takes longer. A sudden brightening could be thermal, electromagnetic, or a combination. A jet pointing sunward could be driven by gas pressure, by recoil from asymmetric sublimation, or by magnetic forces acting on charged dust. To distinguish these possibilities, observers will track the comet continuously for hours, measuring brightness every few minutes, capturing spectra every hour, imaging the coma in multiple filters to separate dust from gas. The data will reveal patterns. If the brightness fluctuates with a period of about 6 hours, the rotation period of the magnetic cloud's helical structure, that is evidence for electromagnetic coupling. If the spectrum shows enhanced ionization, immediately after perihelion, that supports the hypothesis. If polarimetry reveals unusual grain properties, that adds another clue. But even with all this data, certainty may remain elusive. Nature does not always provide clean answers. Comets are complex, and their behavior at perihelion reflects the interplay of dozens of processes: thermal conduction, gas dynamics, radiation pressure, mechanical stress, chemical reactions, and possibly electromagnetic effects. Disentangling these processes requires not just observations but models, computer simulations that incorporate known physics and predict observable outcomes. If the models match the data, confidence grows. If they diverge, we learn where our understanding is incomplete. This is the scientific method in action: observe, hypothesize, predict, test, refine. The cycle continues indefinitely, each iteration bringing us closer to understanding. October 21st is one such iteration. It is not the final word, but it is a step, a moment, when the universe offers us a glimpse behind the curtain, and we either see the pattern or we don't. Either way, we record what we observe, we publish the data, we invite scrutiny, replication, alternative interpretations, and we wait for the next opportunity to test our ideas. 9 days later, on October 30th, 3i Atlas will provide that next opportunity. The interstellar visitor's perihelion is less dramatic than SWAN's, farther from the now, o roteiro ainda não terminou. Estou no capítulo 20 demandas. 22. Faltam apenas 2 capítulos para concluir. Vou finalizar agora com os capítulos 21 e 22, conforme solicitado. Você pediu, no máximo, umas 3 partes e finalize o roteiro. Chapter 21. The Interstellar Witness, October 30, 2025. 9 days after SWAN's perihelion. The solar system has not stopped moving. Earth has completed 1/3 of a lunar month. SWAN, having survived its closest approach, is now receding outward, fading gradually as solar heating weakens. And 3I Atlas, the interstellar visitor, arrives at its own moment of maximum solar exposure. At 0.26 AU, 24 million miles from the Sun, 3I Atlas experiences radiation intensity roughly 15 times greater than at Earth's orbit. This is far less intense than SWAN's perihelion environment, but sufficient to drive significant sublimation if volatile ices remain near the surface. The object has been active since September 29th, when its coma first appeared. Over the past month, the coma has grown steadily, reaching 200,000 miles in diameter by late October. Spectra reveal water vapor, cyanogen and diatomic carbon, molecules consistent with cometary composition, but surprising for an object that spent millions of years in interstellar cold. The question now is whether 3I Atlas will respond to perihelion in the same way SWAN did, whether it will brighten suddenly, erupt unexpectedly, or simply follow the predictable curve of solar heating. If SWAN showed electromagnetic effects on October 21st, and the data from that event is still being analyzed as of today, September 30th, in this narrative's time frame, then 3I Atlas becomes the confirming test. 2 objects, different origins, similar responses. The pattern strengthens. But if SWAN passed perihelion quietly, brightening only as solar heating predicts, then 3I Atlas's behavior becomes less critical. The electromagnetic hypothesis, lacking support from SWAN, would not gain credibility even if the interstellar visitor behaved anomalously. Comets are individuals. 1. Object's eccentricity does not establish a universal mechanism. This asymmetry is frustrating but unavoidable. Positive results, clear evidence of electromagnetic effects, would be compelling. Negative results, no anomalies detected, would be ambiguous, explainable either by the absence of the mechanism or by insufficient sensitivity to detect it. Science often operates in this asymmetric space. Proof is difficult. Disproof is easier, but never absolute. We accumulate evidence, weigh probabilities, and form tentative conclusions that remain open to revision. For 3I Atlas, the observational campaign is similar to SWAN's, but more limited. The object is fainter, magnitude 12.8 on October 30th, requiring telescopes of at least 8 inches aperture to observe visually. Professional observatories in Chile and Hawaii have scheduled time, but fewer hours than for SWAN. The interstellar visitor, while scientifically fascinating, lacks the brightness and accessibility that made SWAN a public spectacle. Amateur contributions are minimal. The object is too faint for casual observation, too distant for detailed imaging with small telescopes. This leaves the burden on professional instruments, which are always oversubscribed, always juggling competing demands. But the data will come. Spectra will be captured. Brightness measurements will be logged. Images will reveal whether the coma remains symmetric or develops asymmetries hinting at non-thermal processes. And then, as the data is analyzed over the following weeks, patterns will emerge or fail to emerge. The electromagnetic hypothesis will gain credibility or fade into the background as an interesting but unsupported idea. This is the rhythm of science. Burst of activity during observational windows, long periods of analysis afterward, papers written, submitted, reviewed, conferences where results are debated, gradual convergence toward consensus, or continued disagreement if the data remains ambiguous. The events of September and October 2025 will occupy researchers for months, possibly years. The timeline is documented. The correlations are noted. But correlation is not causation, and establishing causation requires more than timing. It requires mechanism, reproducibility, and the exclusion of alternative explanations. Perhaps future observations will provide these. Perhaps another bright comet will approach the Sun during a period of high solar activity, allowing researchers to test predictions in real time. Perhaps interstellar object 4I, whenever it arrives, will offer another data point. Or perhaps the September-October 2025 sequence will remain an isolated curiosity, suggestive but inconclusive, a reminder that the universe occasionally assembles events in patterns that invite interpretation but resist definitive explanation. We do not yet know which outcome will prevail. We are too close to the events, too immersed in the data collection phase to see the broader picture clearly. But we will know, eventually. Time filters speculation, preserves data, and allows perspective to emerge. For now, on this final day of October, as 3I Atlas passes perihelion and begins its journey back to interstellar space, we watch, we measure, we record, and we wonder whether the sky has been trying to tell us something all along. Chapter 22. What the silence teaches tonight. I return to the question posed 21 chapters ago. Are we witnessing chaos, or a hidden order older than our instruments? The data may suggest coincidence, but the timing demands scrutiny. We have traced a chain of events from September 26 through October 30th. We have documented correlations between a nova 3,000 light-years away, a solar flare, 2 comets, and an interstellar visitor. We have proposed a mechanism, electromagnetic disturbances propagating through the solar wind, carried by magnetic fields, amplified by plasma instabilities, and identified testable predictions. But we have not proven causation. We have not established that the nova triggered the flare, that the flare triggered the comet outbursts, that the magnetic structures threading the solar wind are responsible for the observed brightenings. We have only assembled the pieces and noted that they fit together more neatly than chance alone would predict. This is not failure. This is progress. Science advances not through immediate certainty, but through progressively refined understanding. We eliminate impossible explanations. We narrow the range of plausible mechanisms. We identify what observations would distinguish competing hypotheses. The September-October 2025 sequence has done this. It has highlighted the heliospheric current sheet as a potentially important influence on cometary activity. It has raised the question of whether distant novas can send electromagnetic signals that propagate through the galactic environment and influence the Sun. It has reminded us that the solar system is not isolated, but embedded in a larger electromagnetic network extending across light years. These ideas are not new. Hannes Alfvén proposed in the 1940s that electric currents flow through space, connecting stars and planets in a vast circuit. His ideas were controversial then, and remain so today. Accepted in some forms, rejected in others, debated endlessly in journals and conferences. What the September-October events provide is fresh data, a new case study, a moment when the universe aligned multiple phenomena in ways that invite electromagnetic interpretation. Whether that interpretation is correct, whether the pattern is real or illusory, will be determined not by this investigation alone, but by the accumulation of future observations. If similar sequences recur, if other comets outburst when crossing disturbed regions of the heliospheric current sheet, if statistical studies reveal correlations between solar flares and distant stellar events, the hypothesis strengthens. If such patterns do not recur, if the September-October sequence remains unique, we acknowledge it as an interesting anomaly and move on. This is the nature of science. Not all questions are answered. Not all patterns are meaningful. Some coincidences are genuine coincidences, statistical flukes that occur precisely because the universe is vast and events are numerous. But some patterns are real, some connections exist, and the only way to distinguish the two is through observation, testing, and the rigorous application of skepticism tempered by openness to unexpected possibilities. The solar system continues its ancient clockwork. SWAN, having survived perihelion, recedes outward, its brightness fading as distance and depletion take their toll. By December, it will be a faint smudge in telescopes, and by March 2026 it will be too distant to observe. Its orbit, calculated from months of positional measurements, indicates it will never return. Like 3I Atlas, SWAN is on a hyperbolic trajectory, bound for interstellar space. 3I Atlas II departs. Its brief visit to the inner solar system, lasting less than 2 years from discovery to departure, provided a glimpse of another world's chemistry. The data, spectra, images, brightness curves, will be analyzed for years, extracting information about volatile composition, surface properties, activity mechanisms. Both objects leave behind questions. Did they respond to electromagnetic disturbances, or did they simply sublimate under solar heating? Were their outbursts driven by external triggers or by internal processes we do not yet fully understand? The answers, if they exist, lie in the data archives, waiting for researchers with the time, tools, and insight to extract them. Novacast 2025 has faded. By late October, it has dropped below naked eye visibility, magnitude 6 and dimming. In a few months, it will return to obscurity, invisible without large telescopes, a white dwarf silently accreting hydrogen from its companion, preparing for the next eruption decades or centuries hence. The Sun remains active. Solar cycle 25 continues its ascent toward maximum, expected in mid-2025. New active regions appear, old ones rotate out of view. Flares erupt, CMEs launch, the solar wind gusts and lulls. The rhythm continues, indifferent to human interpretations, and Earth rotates, orbits, carries its cargo of observers who look upward and wonder. If October passes without anomalies, was it coincidence, or have we simply missed the signal? This question cannot be answered definitively. The universe does not provide certainty. It provides data, and we interpret as best we can, acknowledging the limits of our instruments, our models, our understanding. What we can say with confidence is this: the September-October 2025 sequence was unusual. The timing of events, nova, flare, outbursts, alignments, was precise enough to invite electromagnetic interpretation. The mechanism proposed is plausible, consistent with plasma physics, and testable through future observations. Whether the mechanism is correct remains an open question, but the question is worth asking. And in asking, we learn. We learn that the solar system is more dynamic, more interconnected, more responsive to external influences than simple gravitational models suggest. We learn that comets are sensitive probes of the solar wind's electromagnetic structure. We learn that patterns, when they appear, deserve investigation even when they challenge conventional understanding. And we learn humility. The universe is vast, ancient, complex beyond our current comprehension. We see only fragments, snapshots, correlations that hint at deeper structures we have not yet mapped. But we continue. We observe. We measure. We test. We refine our questions and prepare for the next convergence whenever it may come. The cosmos delivered a 1-2-3 punch in late September 2025. Whether it was chaos or choreography, we may never know with certainty. But we watched. We documented. We wondered. And in wondering, we honor the tradition of every astronomer who has looked upward and asked, what is the universe trying to tell us? Perhaps nothing, perhaps everything. The sky does not answer. It only offers light, motion, patterns that may or may not be meaningful. We watch, we interpret, we wait. And the universe, indifferent and magnificent, continues its ancient dance.